Look up at the night sky on a clear evening, and what do you see? A scattering of stars, perhaps the hazy glow of the Milky Way, a familiar and beautiful tapestry that has inspired humanity for millennia. But what if I told you that everything we can see with the naked eye, every star, every constellation, is merely the decorative flourish on the surface of something infinitely larger and more mysterious? We are about to embark on a journey that will stretch your imagination to its very limits, a voyage beyond the beautiful but deceptively small landmarks we think we know, into a realm of such immense scale that it challenges the very foundations of what we understand about reality itself. Those shimmering clouds of gas and dust that astronomers have poetically nicknamed gassy mountains, the gorgeous nebulas where stars are born, are not our final destination. They are merely the foothills, the starting point of a much grander expedition. Today, we are going to journey past these local marvels to confront the universe's true Leviathans, colossal structures woven into the fabric of space itself. We are talking about galaxy filaments longer than you can possibly conceive, and cosmic voids so vast and empty they defy all logic. These are the architectural foundations of the cosmos, and their sheer existence pushes our scientific models to the breaking point. By the end of our time together, you will not only grasp the staggering scale of these formations spanning hundreds of millions, even billions, of light years, but you will also understand why their discovery is causing such a profound stir within the world of cosmology. These aren't just distant curiosities, they are clues, hints that our current physics might be incomplete, that there are deeper layers of reality waiting to be uncovered. So prepare yourself for an adventure that will take us to the very edge of scientific understanding, a voyage across billions of light years to unveil the universe's most massive structures. To truly begin our voyage, we must first stand in awe of our celestial backyard, where clouds of gas and dust paint the darkness with ethereal light. These are the nebulae, the so-called gassy mountains of the cosmos, and they are far more than just pretty decorations. An emission nebula, like the magnificent Orion Nebula, is a titanic stellar nursery. Its vibrant glow is the result of intense ultraviolet radiation from newborn stars, a process much like a neon sign, energizing the vast clouds of primarily hydrogen gas and causing them to emit their own brilliant light. Then there are reflection nebulae, which act more like cosmic fog, scattering the light from nearby stars to create beautiful, softer blue halos. And we cannot forget the dark nebulae, those silhouetted clouds of dense dust that block the light behind them, carving out dramatic shapes against the starry background like the famous Horsehead Nebula. These regions are the cradles of solar systems. Within their swirling, turbulent hearts, gravity works its magic, pulling together pockets of gas and dust until the pressure and heat become so immense that nuclear fusion ignites. A star is born. The Carina Nebula is a prime example of this chaotic and creative force, a maelstrom of star formation where massive, volatile stars are constantly sculpting their own environment with powerful stellar winds, preparing to seed the galaxy with new elements forged in their furnaces. This is the galactic ecology in action. The life cycle of stars plays out here. They are born from these clouds, they live their lives, and when they die in spectacular supernova explosions, they enrich the surrounding gas with heavy elements that will one day form planets and perhaps life itself. For centuries, these nebulous clouds were both our guideposts and our blinders. They served as beautiful, familiar landmarks in the night sky, but their very presence also obscured the view beyond. The thick dust lanes of our own Milky Way galaxy created a zone of avoidance, a swath of the sky where astronomers could not easily see what lay behind it, effectively creating a hidden frontier in our cosmic maps. We were like early mapmakers who had beautifully charted the coastline, but had yet to venture inland to discover the continents and mountain ranges that lay beyond. These nebulae, for all their grandeur, are the cosmic equivalent of those coastlines. They are immense, with the Orion Nebula stretching over 24 light-years across. But as we prepare to push off from these shores, we must recalibrate our sense of scale. The structures we are about to encounter make these glowing clouds seem like the tiniest of foothills at the base of a mountain range that spans the entire observable universe. But to truly grasp the enormity of what lies ahead, we must first perform a profound shift in our perspective, a complete recalibration of scale. The Orion Nebula, a titan in our own celestial neighborhood, measures about 24 light-years across. Wrap your mind around that distance for a moment. A single light-year is almost 6 trillion miles. Now, prepare to have your conception of size stretched to its absolute limit. The cosmic structures we are now turning toward are not measured in dozens or even thousands of light-years. Their vastness is counted in hundreds of millions of light-years. To put that into perspective, if our entire Milky Way galaxy, itself 100,000 light-years wide, were scaled down to the size of a dinner plate, these massive formations would be the size of an entire continent. We are moving from the scale of individual mountains to the scale of the entire planet's tectonic architecture. This grand architecture is known as the cosmic web. It is not a metaphor, it is the fundamental skeleton of the universe. Picture an immense three-dimensional spiderweb, or the intricate, delicate lattice of a sponge. Across unimaginable voids of empty space, galaxies are not scattered randomly. Instead, they are drawn into these enormous filaments, these great walls and threads of matter that stretch across the cosmos, connecting at dense nodes where thousands of galaxies swarm together in massive clusters. In between these brilliant structures lie the correspondingly vast cosmic voids, regions of breathtaking emptiness that make up most of the universe's volume. This is the true large-scale structure of the universe, a web of matter on a scale so grand it defies easy analogy. How on Earth, or rather, how from Earth, do astronomers possibly map something so immense and largely invisible? The primary tool for this cosmic cartography is the redshift survey. As the universe expands, the light from distant galaxies is stretched, shifting its wavelength toward the red end of the spectrum. By meticulously measuring this redshift for millions of galaxies, astronomers can not only determine their distance from us, but also their velocity through space. Projects like the Sloan Digital Sky Survey have painstakingly catalogued the positions of over 3 million galaxies, and when those positions are plotted in 3 dimensions, the result is nothing short of breathtaking. A map that reveals the cosmic web in stunning detail, a vast celestial network with galaxies tracing its invisible line. This shift in understanding was championed by cosmologists like J. Richard Gott, who, along with his colleagues, first began to describe the universe in these terms. They recognized that the cosmos is not a simple, homogeneous soup of galaxies but is instead structured, organized into this complex web-like pattern. This realization fundamentally transforms our understanding of our place in the universe. We are not looking out from a random point in a random collection of stars. We are residing within one filament of this immense web, our local group of galaxies a mere speck on a single strand of this cosmic tapestry. This new perspective immediately forces upon us a series of profound and thrilling questions. What cosmic forces could possibly sculpt matter on such an incomprehensible scale? What ancient processes in the infancy of the universe laid down the blueprint for this web? The journey to find these answers leads us directly to the discovery of the first true cosmic Leviathan. And it was in the 1980s that this abstract concept of a cosmic web suddenly snapped into sharp, shocking focus with a discovery that sent ripples through the entire field of cosmology. The story begins with a relatively modest-sounding project at the Harvard-Smithsonian Center for Astrophysics, known as the CF, a redshift survey. Led by the determined astronomers Margaret Geller and John Huckra, the goal was straightforward yet ambitious: to measure the redshifts, and therefore the distances, to a large sample of galaxies in a specific slice of the sky. They were not hunting for giants. They were simply trying to create a more three-dimensional map of our local universe. But what their painstaking work revealed was anything but modest. As they plotted the positions of each galaxy, a pattern began to emerge that was so immense, so unexpected, it forced everyone to reconsider the very architecture of the cosmos. They had discovered the CFA2 Great Wall, a monolithic filament of galaxies that stretched across the surveyed region like a colossal celestial backbone. This was not a mere cluster of galaxies. It was a vast, interconnected sheet, a great arc of galactic concentration measuring over 500 million light-years in length, 200 million light-years in width, and a staggering 15 million light-years in thickness. To grasp that scale, try to imagine a structure so long that a beam of light, traveling at the universe's ultimate speed limit, would take 500 million years to go from one end to the other. If our entire Milky Way were the size of a standard dinner plate, this great wall would be as wide as the entire continental United States. It was, by a significant margin, the largest single structure ever identified at that time, a true Leviathan in the cosmic dark. The discovery sent a jolt of awe and disbelief through the scientific community. For decades, the prevailing cosmological principle had been a bedrock of modern astronomy. This principle states that on sufficiently large scales, the universe should look roughly the same everywhere. It should be homogeneous and isotropic, meaning no matter where you are or what direction you look, the overall distribution of matter should appear uniform. The existence of the Great Wall seemed to directly challenge this fundamental assumption. Here was a structure of such pronounced density and scale that it appeared to be a glaring exception to the rule of large-scale uniformity. It was far larger than what many theorists believed could have formed through gravitational attraction alone in the time since the Big Bang. How could gravity have pulled together so much matter into one specific, gigantic structure in just under 14 billion years? The Great Wall was not just a discovery, it was a profound anomaly, a cosmic puzzle that sparked intense debate and forced a re-evaluation of our models for how structure forms. Margaret Geller herself captured the sheer wonder of the moment, famously describing the map of the universe as resembling nothing less than soap bubbles, with galaxies coating the surfaces of vast empty voids. The CFA2 Great Wall was the most dramatic and defining membrane of those bubbles. It was a watershed moment, a before and after dividing line in the history of cosmology. Before the wall, our view of the universe's large-scale structure was blurry and theoretical. After its discovery, the cosmic web was no longer just a compelling idea. It was an observable, measurable reality. It proved that the universe was lumpy on scales no one had previously dared to imagine, and it fundamentally shifted the goalposts for astronomers. If a structure this colossal could exist, what else was out there waiting to be found? The Great Wall didn't just answer questions, it flung the door wide open for a new era of exploration, setting the stage for the hunt for even larger, more perplexing giants hidden in the depths of space and time. Yet for every great wall and dense filament in the cosmic web, there exists a corresponding and equally critical opposite, a vast, breathtaking emptiness. If the universe's structure is a sponge, then these are the holes. If it is a web, these are the gaps between the threads. Astronomers call them cosmic voids, and to understand the full majesty of the cosmic architecture, we must turn our attention away from the bright, crowded cities of galaxies and toward these immense, silent deserts of space. A cosmic void is not just a slightly emptier patch of the universe. It is a region of profound underdensity, a bubble of nothingness that can stretch for hundreds of millions of light years and contain only a handful of isolated, lonely galaxies. To put that scale into a human perspective, if our Milky Way were a single grain of sand, a typical void would be an empty sphere the size of a professional sports stadium. These voids are not rare anomalies. They are the dominant feature of the universe by volume, making up an astonishing 80 to 90% of all space. While our attention is naturally drawn to the brilliant lights, the universe is, in fact, mostly composed of these vast, dark, and empty expanses. The formation of these voids is a direct and elegant consequence of gravity's relentless work over billions of years. In the very early universe, matter was distributed almost, but not perfectly, evenly. There were tiny quantum fluctuations in density. Regions that were ever so slightly denser than average had a stronger gravitational pull, acting like anchors that began to attract more and more matter from their surroundings. Conversely, the regions that started out with just a fraction less material had a weaker gravitational grip. As the eons passed, this process created a great cosmic sorting mechanism. Matter steadily drained away from these underdense regions, flowing along gravitational gradients into the waiting filaments and nodes of the web. The voids were left behind, expanding and emptying out as the universe evolved. They are not static holes, they are dynamic entities growing emptier and larger over time as their boundaries are defined by the inward collapse of matter everywhere else. This process has been beautifully illustrated by the work of astronomers like Rien van der Weygaert, who poetically refers to voids as the universe's deserts. This is a perfect analogy. Just as a desert on Earth is defined by its lack of water and its profound impact on the ecosystems at its edges, a cosmic void is defined by its lack of matter and its powerful influence on the galaxies that border it. The few galaxies that do find themselves inside a void are often strange, malformed objects, isolated from the dense environments where galaxies typically collide and merge. These void galaxies can be ancient, unevolved, and often fizzle out early, lacking the fresh gas needed to form new stars. They are the hermits of the cosmos, living quiet, solitary lives in the great emptiness. But the importance of voids extends far beyond being mere curiosities or empty backdrops. They have become one of the most powerful tools cosmologists have for studying the most mysterious forces in the universe, particularly dark energy. The accelerated expansion of the universe, driven by dark energy, doesn't just affect galaxies individually, it affects the entire architecture of the cosmic web. Because voids are mostly empty, the pressure of dark energy dominates their evolution more easily than in matter-rich regions. Think of it like this: in a dense forest, the trees support each other and resist the wind. But in a wide open field, the wind has nothing to stop it. Similarly, within a void, dark energy meets little resistance from matter's gravity, allowing the void to expand outward more rapidly. By meticulously measuring the shapes, sizes, and growth rates of thousands of these voids, scientists can take the universe's temperature, gauging the strength of dark energy and how it has changed over cosmic history. These great nothings, therefore, are providing some of the most telling clues about the ultimate fate of everything. If the discovery of the CFA2 Great Wall was the moment astronomers first glimpsed the skeleton of the cosmic web, then the Sloan Great Wall was the moment they saw the full, terrifying scale of that skeleton. Just over a decade after the initial surveys, a new generation of technology and ambition gave rise to an even more ambitious project, the Sloan Digital Sky Survey. This was not a small, targeted study of a single slice of the sky. This was an industrial-scale, systematic census of the cosmos, an effort to map in meticulous detail a full quarter of the entire night sky. Using a dedicated 2.5-meter telescope in New Mexico, equipped with a revolutionary digital camera and a sophisticated spectrograph that could measure the redshifts of hundreds of galaxies simultaneously, the Sloan survey began to collect data on a scale previously unimaginable. It was this unprecedented fire hose of information, the precise positions, distances, and colors of millions of celestial objects, that would soon reveal a structure so vast it pushed the very definition of structure to its breaking point. The Sloan Great Wall, officially identified in 2003, is a cosmic Leviathan that utterly dwarfs its predecessor. This is not merely a larger version of the same thing, it is a different category of object entirely. Where the CFA2 wall spanned a still incomprehensible 500 million light-years, the Sloan wall stretches for an almost absurd 1.4 billion light-years. To travel from one end of this structure to the other at the speed of light would take you 1.5 times the current age of the entire universe. It contains not dozens or hundreds, but many thousands of galaxies, all gravitationally linked into a single, coherent filamentary wall. Its discovery was not the result of a lone team poring over photographic plates, but the product of a massive international collaboration, fueled by terabytes of digital data and the immense processing power of supercomputers needed to crunch the numbers and render the three-dimensional map. This technological leap is what truly separates the two discoveries. The CFA survey was a monumental manual effort. The Sloan survey is a feat of automated, data-driven astronomy. The spectrograph on the Sloan telescope didn't just look at one galaxy at a time. Its hardware was designed to drill tiny holes in a metal plate corresponding to the positions of hundreds of target galaxies, thread optical fibers through each hole, and then funnel the light from all of those galaxies simultaneously into its sensors. In a single night, it could gather more redshift data than the entire CFA survey had collected in years. This raw data was then processed by algorithms and visualized in powerful simulations, allowing astronomers to fly through this digital universe and spot patterns that would have been invisible on a two-dimensional plot. The Sloan Great Wall emerged from this digital sea not as a faint suggestion, but as a stark, undeniable reality, a mountain range in the data that could not be ignored. And its immense size is precisely what makes it so deeply troubling to theorists. According to our standard model of cosmology, known as the lambda cold dark matter model, there is a fundamental upper limit to how large a gravitationally bound structure can become. This limit is set by the age of the universe and the initial conditions laid down by inflation. The model predicts that while the cosmic web should have filaments and walls, they should not grow much larger than about 1.2 billion light-years across. The Sloan Great Wall at 1.4 billion light-years doesn't just nudge against this limit, it crashes right through it. Its very existence suggests that either our measurements of the initial conditions are slightly off, that there is something we don't understand about how dark matter and dark energy sculpt the web, or that the primordial universe was somehow lumpier on the largest scales than our theories of inflation predict. It is a beautiful, data-rich anomaly that sits right at the heart of modern cosmology, a constant reminder that our best models are still works in progress. Yet just when we thought our maps of the cosmic web were nearing completion, an anomaly of such staggering proportions emerged that it threatened to redraw them entirely, pushing our understanding of cosmic structure to the absolute brink. If the Sloane Great Wall seemed to challenge the rules, the Hercules Corona Borealis Great Wall appears to shatter them completely, proposing a structure so vast it seems to defy the very logic of the universe itself. This isn't a discovery made by mapping galaxies. It was uncovered by tracing the most violent and brilliant explosions in the cosmos, gamma-ray bursts. These bursts are the death cries of the most massive stars, fleeting events that release more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifetime. For decades, astronomers have catalogued these explosions, and a team led by Istvan Horvath noticed something peculiar. The distribution of these bursts across the sky was not random. There was a significant and startling concentration of them in the constellations of Hercules and Corona Borealis, a region of the sky spanning an almost unimaginable distance. By analyzing the redshifts of these gamma-ray bursts, which give us their distances, the team made a jaw-dropping inference. They weren't just looking at a random cluster of events. They were potentially looking at the signature of an underlying structure, a vast wall of galaxies so immense that it could be nearly 10 billion light-years across at its longest dimension. Let that number sink in for a moment. 10 billion light-years. The observable universe itself is only about 93 billion light-years wide. This would mean a single structure, a coherent concentration of matter, occupies more than 10% of the entire observable cosmos. The scale is so preposterously large that it immediately invites intense skepticism and scrutiny, as any good frontier discovery should. How could such a thing possibly exist? The cosmological principle, the foundational idea that the universe should appear roughly uniform in all directions at the largest scales, would not just be challenged by this object, it would be rendered utterly obsolete. If this great wall is real, then the universe is not homogeneous. It has a discernible, massive structure on a scale we never thought possible, implying that matter is distributed in a way that our standard models of cosmology simply cannot account for. The method of its discovery is both ingenious and indirect, which is a key reason for the ongoing debate. Gamma-ray bursts are not galaxies, they are transient events. The team, including Horvath and his colleague John Hakila, argued that these brilliant flashes are not evenly distributed through space, but are instead associated with regions of active star formation. Therefore, a dense concentration of them likely traces an equally dense concentration of galaxies, a massive filament of the cosmic web. They used sophisticated statistical analyses to show that the clustering of bursts in this region was highly unlikely to be a chance occurrence. As Horvath himself stated, the Hercules Corona Borealis Great Wall is an extremely large structure. Its size is the problem. According to the principles of cosmology, such a large structure shouldn't exist. And this is where the scientific process unfolds in real time. Many cosmologists remain deeply skeptical, arguing that this alleged wall could be a statistical fluke, a classic case of apophenia seeing patterns in random noise. The dataset of gamma-ray bursts is still relatively small, and it's possible that with more observations, this apparent clustering could vanish. Others propose it could be a projection effect, an illusion created by multiple structures at different distances lining up along our line of sight, fooling us into perceiving a single, connected entity. The controversy is a perfect example of how science cautiously grapples with extraordinary claims, demanding extraordinary evidence. Yet, the very possibility of its existence is electrifying. It forces us to confront the most fundamental questions about the cosmos. Did the process of inflation, which smoothed out the early universe, leave behind primordial wrinkles far larger than we predicted? Could there be unknown physical processes that allowed gravity to work over these mind-boggling distances? Or does this hint that we need to reconsider our entire understanding of the universe's topology? The Hercules corona Borealis Great Wall, whether it is ultimately confirmed or refuted, stands as a powerful symbol of the frontier nature of cosmology. It represents the thrilling, unsettling, and utterly captivating reality that the universe is still capable of presenting us with mysteries that defy our current frameworks, ensuring that the journey of discovery is far from over. But as we stand in awe of these cosmic leviathans, from the great walls to the vast voids, a profound and unavoidable question emerges. What is the hidden architect behind this grand design? If gravity is the sculptor's hand, then what is the material it is shaping? The stunning answer is that the beautiful galaxies and glowing gas we see are merely the decorative finish on a framework built from something we cannot see at all. This invisible substance, known as dark matter, is the true master builder of the cosmic web, the hidden hand that has guided the formation of every massive structure we've explored. Dark matter is perhaps the most enigmatic and yet essential component of our universe. It makes up roughly 27% of the entire cosmos, a staggering amount compared to the mere 5% that constitutes all the ordinary matter, the stars, planets, and nebulae we are familiar with. We cannot see it because it does not emit, absorb, or reflect any light. It interacts with the visible universe solely through the force of gravity. This ghostly nature is what makes it so difficult to detect directly, but its gravitational influence is unmistakable and overwhelming. It is the gravitational glue that holds galaxies together, the unseen framework upon which the entire visible universe is constructed. Without its immense gravitational pull, galaxies would fly apart, and the cosmic web as we know it would simply not exist. The first compelling evidence for this invisible component came not from looking at the largest scales, but from studying the motion of stars within individual galaxies. In the 1970s, the brilliant astronomer Vera Rubin was meticulously measuring the rotation curves of spiral galaxies, that is, how fast stars orbit around the galactic center at different distances. According to the laws of gravity and the visible mass of stars and gas, stars on the outer edges of a galaxy should orbit much more slowly than those near the center, just as Pluto moves more sluggishly around the Sun than Mercury does. But Rubin's observations revealed something astonishing and paradigm-shifting. Stars at the far outskirts of galaxies were orbiting just as fast as those near the core. This could only mean one thing: there was far more mass in the galaxy than anyone could see, distributed in a massive, invisible halo that extended far beyond the visible edge of the galaxy. This halo of dark matter provides the extra gravitational pull to keep those outer stars whipping around at high speed. Rubin's work provided the first robust, observational proof that the universe was dominated by something we could not see, a discovery that fundamentally reshaped the field of cosmology. This concept of dark matter halos is the key to understanding the entire large-scale structure of the universe. From the very beginning, dark matter was the primary ingredient. In the hot, dense early universe, while ordinary matter was a chaotic plasma constantly buffeted by radiation pressure, dark matter, being unaffected by light, was free to start clumping together immediately under its own gravity. It began to form a vast, invisible scaffolding, a cosmic skeleton, with denser knots and long, connecting filaments. Billions of years later, when the universe had cooled enough for ordinary atoms to combine into gas, this gas felt the powerful gravitational pull of the pre-existing dark matter network. It flowed down along these invisible gravitational gradients, cooling and condensing at the intersections of the filaments, where it eventually collapsed to form the first stars and galaxies. The brilliant galaxies we observe today are not randomly scattered. They precisely trace out the underlying hidden architecture of the dark matter web. We see the lights of the cities, but the dark matter is the continent upon which they are built. The most powerful tool for visualizing this incredible process is the cosmological simulation. Projects like the landmark Millennium simulation run by the Virgo Consortium are essentially universe-generating machines. They use the immense processing power of supercomputers to model the gravitational interaction of billions of dark matter particles across almost the entire age of the universe. When researchers run these simulations based on our best models of physics and the initial conditions from the cosmic microwave background, the result is nothing short of magical. Over virtual billions of years, the particles spontaneously collapse into an intricate cosmic web of halos and filaments, a digital universe that looks uncannily like the maps we create from galaxy redshift surveys. These simulations don't just confirm the role of dark matter, they demonstrate that it is the indispensable ingredient. Without including dark matter in the equations, the simulations produce a bland, smooth universe that looks nothing like the richly structured cosmos we actually observe. The presence of this invisible matter is the only way to explain the magnificent web-like tapestry of galaxies that fills our telescopes. But for all its power and prevalence, dark matter is only half the story. It provides the gravitational blueprint, the invisible skeleton, but it cannot build the glittering cities of stars and galaxies on its own. For that, we need the universe's visible, tangible building blocks, baryonic matter. This is the term physicists use for the ordinary stuff you and I are made of: the protons, neutrons, and electrons that constitute every atom, every star, every planet, and every nebula we can see. It is the luminous tip of a very deep, very dark cosmic iceberg. While dark matter makes up 27% of the universe and dark energy another 68%, baryonic matter is the remaining 5%. It is a stunning realization that everything we have ever observed with every telescope, every beautiful image that has ever captured our imagination, represents just a tiny fraction of what is actually out there. Yet this 5% is far from a passive passenger in the cosmic journey. Once the dark matter scaffolding was firmly in place, its immense gravitational pull began to act like a cosmic shepherd, guiding the flows of ordinary matter. In the early universe, this baryonic material existed as a searingly hot, diffuse plasma, so energetic that atoms couldn't even form. But as the universe expanded and cooled, this hot gas was inexorably drawn into the gravitational wells of the dark matter filaments and halos. Imagine a vast, invisible network of valleys and mountains, and then picture a fine mist of water being pulled by gravity to flow into the deepest valleys, collecting into lakes. That is precisely how baryons behave, streaming along the contours of the dark matter cosmos. This is where the story gets truly dynamic. As the gas flows into these dark matter valleys, the junctions where filaments meet it doesn't just accumulate quietly. It collides, it compresses, and it heats up to incredible temperatures, often reaching millions of degrees and glowing intensely in X-ray light. These are the intracluster mediums found at the hearts of giant galaxy clusters, vast reservoirs of superheated gas that contain more mass than all the stars in all the cluster's galaxies combined. But to form stars, this gas needs to cool down. Dense pockets within these clouds eventually radiate away their heat, allowing gravity to take over and trigger the collapse that births new stars. This is the beautiful, cyclical process that lights up the cosmic web, transforming invisible gravitational potential into the brilliant fires of galaxies. However, this process is not a one-way street. The universe has its own built-in regulatory systems, powerful feedback mechanisms that prevent all the gas from immediately collapsing into stars. The most dramatic of these is the supernova. When a massive star reaches the end of its life and explodes, it does so with unimaginable violence, blasting its outer layers back into space at tremendous speeds. This explosion enriches the surrounding gas with heavy elements like carbon, oxygen, and iron, the very elements necessary for planet formation and life. But it also heats the gas and drives powerful shockwaves through it, preventing it from cooling and collapsing again too quickly. It's a cosmic form of temperance, a self-regulating cycle of creation and destruction that ensures star formation proceeds at a measured pace. An even more extreme regulator sits at the center of many galaxies, the supermassive black hole. When these monsters are actively feeding on infalling gas, they become active galactic nuclei, some of the most energetic objects in the universe. The process doesn't just create a brilliant quasar, it also generates powerful jets of particles and radiation that shoot out from the galactic center for hundreds of thousands of light years. These jets pump enormous energy back into the surrounding gas reservoir, heating it so effectively that it cannot cool down to form new stars. This feedback process is crucial for explaining why giant elliptical galaxies, often found at the crowded centers of clusters, have mostly stopped forming new stars. Their central black holes effectively shut down their own fuel supply in a spectacular outburst of self-sabotage. This intricate dance between gravity's pull and feedback's push is what sculpts the visible universe we see, ensuring that the glittering structures tracing the dark matter web are not just static paintings but dynamic, evolving ecosystems. To truly understand the origin of the cosmic web's grand architecture, we must journey back in time to the universe's very infancy, to a moment frozen in light that serves as our most profound window into the past. This is the cosmic microwave background, or CMB, and it is nothing less than the oldest photograph ever taken. Imagine capturing an image of the entire cosmos, not at a few billion years old, but at a mere 380,000 years of age, a cosmic newborn. This is precisely what the CMB represents, the residual glow from the Big Bang itself, a faint whisper of radiation that has been cooling and stretching as the universe expanded for over 13 billion years, now permeating all of space. The story of this primordial light begins when the universe was a searingly hot, dense soup of particles and energy. For its first several 100,000 years, it was so hot that atoms couldn't form. Electrons and protons were ripped apart, existing as a chaotic, opaque plasma, constantly scattering light. If you had been there, you would have seen nothing. The universe was a blinding, featureless fog. But then, as expansion continued, the cosmos cooled just enough for a monumental transition to occur. Electrons finally combined with protons to form the first neutral hydrogen atoms. In that instant, the constant scattering stopped. The universe suddenly became transparent, and light was set free to travel across the cosmos for the very first time. That first flash of light, once brilliant and hot, is what we detect today as the CMB. Its waves stretched by the expansion of the universe over eons into the microwave part of the spectrum, a cool relic just 2.7 degrees above absolute zero. But the true magic of the CMB isn't just its age, it's its incredible detail. When we point our most sensitive instruments at this microwave glow, we don't see a perfectly smooth and uniform blanket. Instead, we see a tapestry of tiny temperature fluctuations, minute variations of just 1 part in 100,000. These tiny ripples, these anisotropies, are the most important part of the story. They represent the seeds of all structure in the universe. The slightly warmer spots are regions of space that were ever so slightly denser than average. the cooler spots were slightly emptier. These minuscule differences in density were imprinted onto the fabric of spacetime by quantum fluctuations in the universe's first fraction of a second, and they were frozen into place by the release of the CMB light. This is the universe's genetic code, and within it lies the blueprint for every galaxy, every cluster, every filament, and every void we see today. Mapping this blueprint with exquisite precision has been one of the greatest triumphs of modern cosmology, spearheaded by space-based observatories like the Planck satellite. Launched by the European Space Agency, Planck spent years scanning the entire sky with unmatched sensitivity, measuring these temperature variations to within a millionth of a degree. The resulting map is a Rosetta Stone for the cosmos. Each tiny fluctuation is a gravitational well in waiting. The slightly denser patches had a tiny bit more gravity, and over the next billions of years, that extra gravitational pull acted like a magnet, slowly and relentlessly drawing in more and more matter from the surrounding regions. Dark matter, which had already begun to clump, provided the underlying scaffold, but these baryonic density seeds defined where the future bright galaxies would eventually coalesce. The magnificent cosmic web, with its great walls and vast voids, is simply the CMB's faint pattern amplified to an almost unimaginable degree by the patient, persistent force of gravity. The Nobel Prize-winning cosmologist George Smoot famously described the CMB as seeing the face of God. But a more practical and equally powerful description is that it is the blueprint of the universe. The patterns Planck measured are not random. Their statistical properties match the predictions of our inflationary model of the Big Bang with stunning accuracy. The sizes and distribution of the hot and cold spots precisely predict the statistical distribution of galaxies and clusters we observe in the universe today. It is a direct causal link from the quantum realm to the cosmic scale, a validation that we are on the right track in understanding the universe's evolution. By studying this fossil light, we are effectively doing cosmic archaeology, digging back through time to witness the initial conditions that gave rise to everything we see. Without this primordial imprint, the gravitational instability that built the universe would have had nothing to work with. The cosmos would have remained a perfectly smooth and perfectly boring expanse of nothingness. The CMB is the ultimate origin story, the moment the dice were loaded for the magnificent, structured universe we inhabit. But how did those tiny, almost imperceptible ripples in the cosmic microwave background come to be? What process in the universe's very first moments could have planted such perfectly calibrated seeds? The answer lies in one of the most profound and elegant theories in all of cosmology, cosmic inflation. This idea proposes that the universe underwent a period of unimaginably rapid, exponential expansion in the first fleeting fraction of a second after the Big Bang. To grasp the scale of this event, imagine a subatomic particle smaller than a single proton suddenly swelling to the size of an entire galaxy, and doing it all in less time than it takes for light to cross that proton. This wasn't just fast expansion, it was a violent, inflationary stretching of the very fabric of spacetime itself. The concept of inflation was first proposed in the 1980s by physicist Alan Guth as a way to solve several major puzzles that the standard Big Bang model left unanswered. Why is the universe so remarkably flat? No matter where we look, the geometry of the cosmos appears almost perfectly Euclidean. Why is the universe so uniform? The temperature of the cosmic microwave background is the same in opposite directions of the sky, even though those regions could never have been in thermal contact according to the standard model. Guth's brilliant insight was that a period of ultra-fast expansion could solve both problems at once. Imagine taking a tiny, subatomic patch of the early universe that was already in thermal equilibrium, a patch that was smooth and uniform. Inflation would then stretch this tiny patch to a size larger than our entire observable universe. This process would iron out any primordial wrinkles, rendering the geometry flat and the temperature uniform, just as we observe. As Guth himself put it, inflation offers the universe the ultimate free lunch, creating a vast, smooth expanse from almost nothing. However, the most crucial gift of inflation was not just creating a smooth universe, but also imprinting it with the faint, necessary imperfections that would become the blueprint for all structure. According to quantum mechanics, empty space is not truly empty. It is a seething, bubbling foam of virtual particles constantly flickering in and out of existence. These are quantum fluctuations. In the unimaginably dense environment of the primordial universe, these tiny fluctuations were not confined to the microscopic world. The violent, exponential expansion of inflation acted like a cosmic amplifier, stretching these subatomic quantum jitters across astronomical distances. A tiny fluctuation in energy density that was once smaller than an atom was suddenly inflated to a scale of hundreds of thousands of light-years. This process transformed microscopic quantum noise into macroscopic classical density variations, the very same variations we now see as the temperature fluctuations in the CMB. In this breathtakingly elegant mechanism, the seeds for giant galaxy clusters were sown by the random twitches of the quantum vacuum. This inflationary stretching also produced a very specific, testable prediction about the nature of these seeds. It predicts that the initial density fluctuations should be nearly scale invariant. This means that the relative difference in density between regions should be roughly the same, regardless of the size of the region you're looking at. Whether you examine a patch of space that will eventually become a single galaxy or a massive supercluster, the initial amplitude of the fluctuation is almost identical. This is a profound and unique signature. It's why the universe has structure on every scale we can observe, from the tiniest dwarf galaxies to the largest walls and filaments. The incredible precision of the Planck satellite's measurements of the CMB revealed a spectrum of fluctuations that matches this scale-invariant prediction with stunning accuracy, providing what many cosmologists consider the strongest evidence we have that a period of inflation indeed occurred. The development of inflation theory was greatly advanced by the work of physicists like Andre Linde, who introduced the concept of chaotic inflation. This model suggests that inflation might not be a one-time event but could be eternal, with different regions of space-time undergoing inflation at different times, potentially giving rise to a vast multiverse, an infinite froth of bubble universes, each with possibly different physical constants. While this remains a highly speculative idea, it highlights how inflation has opened doors to some of the most profound questions about reality. It implies that our entire observable universe, all 93 billion light-years of it, might be just a single bubble in a much grander, perhaps infinite, meta-universe that we can never see. This theoretical framework is the indispensable foundation for our entire understanding of cosmic evolution. It provides the crucial link between the mysterious quantum world and the classical cosmos we inhabit. Inflation takes the simple, smooth initial conditions of the Big Bang and, by stretching the fabric of reality itself, magnifies the faintest quantum whispers into the gravitational seeds that gravity would later use to build the entire cosmic web. Without this explosive initial growth spurt, the universe would lack the necessary irregularities for galaxies to form. It would remain a vast, dark, and featureless void. Inflation is the mechanism that transformed a universe of ultimate simplicity into one of magnificent complexity, setting the stage for everything that was to follow. With the cosmic microwave background providing the initial blueprint and inflation setting the stage, the universe was poised for its next great act, the patient, relentless construction of its large-scale architecture. This magnificent transformation from a nearly smooth primordial soup to a complex cosmic web is driven by one of the most fundamental forces in nature, gravity. This process, known as gravitational instability, is the slow-motion engine that has been building the universe's structures for over 13 billion years, turning those faint whispers of density into the great walls and voids we observe today. Imagine a perfectly flat, sandy plain stretching to the horizon. Now imagine a single, tiny mound of sand, just a few grains higher than its surroundings. This minuscule hill seems insignificant, but it has a gravitational advantage. As wind blows across the plain, specks of dust are slightly more likely to settle on the mound than on the flat ground around it. Over centuries, this effect is imperceptible, but over millions of years, that tiny mound steadily gathers more material, growing slowly into a larger hill. Given enough time, that hill becomes a mountain, its immense mass now pulling in material from even greater distances. This is the essence of gravitational instability. In the early universe, the slightly denser regions revealed by the CMB were those tiny mounds of sand in the smooth cosmic plane. Their minuscule extra-gravitational pull acted as a magnet, ever so slowly drawing in more dark matter and gas from the surrounding regions. The true magic of this process lies in its patient, cumulative nature. For the first several 100 million years after the Big Bang, the growth of these structures was agonizingly slow. The gravitational differences were so tiny that the expansion of the universe almost overwhelmed them. But gravity is persistent and never turns off. As each overdense region pulled in a little more matter, it became slightly denser, which increased its gravitational pull, allowing it to attract matter even more effectively. This is a powerful positive feedback loop, a snowball effect operating on a cosmic scale. What began as a quantum fluctuation of 1 part in 100,000 was gradually amplified into a vast gravitational well capable of anchoring an entire galaxy cluster. The great filaments of the cosmic web formed along the ridges where these gravitational potentials met, like water draining into a continent-wide river system, while the regions that started out slightly emptier, the underdensities evolved into the vast cosmic voids as matter steadily drained away from them. A critical factor that supercharged this entire process was the unique nature of dark matter. Remember, in the universe's first few 100,000 years, ordinary matter, the baryons, was a hot, ionized plasma. This plasma was constantly buffeted by the intense pressure of radiation, which effectively kept it from collapsing smoothly. It was like trying to build a sandcastle in a storm. The waves of radiation kept washing away any attempt for the gas to clump together. Dark matter, however, is collisionless. It does not interact with light or radiation at all. It feels only gravity. This meant that while the baryonic plasma was being pushed around, the dark matter was free to immediately begin responding to gravity's gentle tug. It started collapsing into those primordial overdensities right away, forming a vast, invisible scaffolding of dark matter halos and filaments long before the first stars could ever form. This head start was absolutely crucial. By the time the universe had cooled enough for atoms to form and the radiation pressure to drop, the moment of recombination when the CMB was released, the dark matter had already laid down the foundational framework for the cosmic web. The ordinary matter, now finally free from the radiation's push, simply flowed into the gravitational wells that the dark matter had already prepared. This is why the cosmic web we see today, traced by glowing galaxies, so precisely mirrors the underlying distribution of dark matter. The dark matter provided the gravitational blueprint, and the baryons simply followed the instructions, cooling and collapsing at the nodes of this invisible network to form the stars and galaxies that light up the structure. Without dark matter's early and unimpeded collapse, gravitational instability would have progressed far too slowly, and the universe would not have had enough time to form the magnificent, large-scale structures we see today. This invisible hand was the indispensable architect, guiding the growth of cosmic giants from the tiniest of ripples. Of course, we have the theory and the observations, but how do we connect the two? How do we test our grand ideas about dark matter and gravitational collapse without being able to run the experiment of the universe a second time? The answer lies in one of the most powerful tools of modern cosmology, the creation of digital universes inside the world's most powerful supercomputers. These are known as n-body simulations, and they allow us to witness billions of years of cosmic evolution unfold in a matter of weeks or even days. The core principle is both simple and profoundly complex. The N in n-body simulation stands for the number of particles you are tracking, and that number is astronomically large. Scientists begin by programming a virtual box that represents a chunk of the universe. They then fill this box with millions or even billions of particles. These particles are not individual stars or galaxies. At that scale, the computation would be impossible. Instead, each particle represents a huge clump of dark matter, perhaps with the mass of an entire dwarf galaxy. The simulation then sets these particles in motion according to the only rule that matters on this scale, the law of gravity. Every single particle exerts a gravitational pull on every other particle in the box. Calculating these interactions for billions of particles is one of the most computationally intensive tasks imaginable, requiring algorithms that can cleverly approximate the forces between distant groups to make the math feasible. Over virtual millions of years, the simulation runs forward, and researchers simply watch what happens. They are testing a fundamental question. If our theories about dark matter, gravity, and the initial conditions from the CMB are correct, what should the universe look like today? The results have been nothing short of revolutionary. Landmark projects like the Millennium Simulation, run in 2005, and its more advanced successor, the Illustris Simulation, have produced virtual cosmos that are eerily reminiscent of our own. The Millennium Simulation focused primarily on dark matter, tracing the evolution of 10 billion particles over more than 13 billion years of cosmic time. When researchers looked at the final result, they saw it, an intricate cosmic web of dark matter filaments and halos, a digital universe that looked statistically identical to the maps being created by galaxy redshift surveys. It was a stunning validation that the lambda-cold dark matter model could indeed produce the large-scale structure we observe, but Illustris took this a monumental step further. It wasn't just about dark matter, it incorporated the complex physics of ordinary baryonic matter, the gas, the stars, and the supermassive black holes. This added a whole new layer of incredible detail and challenge. The simulation had to account for the hydrodynamics of gas, how it heats up, cools down, and forms stars. It had to model the explosive feedback from supernova and the powerful jets erupting from active galactic nuclei, which can heat surrounding gas and shut down star formation. When the team, led by astrophysicist Volker Springel, ran the simulation, they were able to watch not just the invisible dark matter scaffold form, but also see galaxies emerge within it. The virtual universe produced spiral galaxies, ellipticals, galaxy clusters, and vast, empty voids. The simulated galaxies even had realistic sizes, masses, and chemical compositions. For the first time, a computer simulation didn't just produce a statistical match. It created a universe that you could fly through and recognize. The power of these digital universes is that they act as a crucial bridge between theory and observation. They allow us to perform experiments that are impossible in the real world. We can ask, what would the universe look like if dark matter were slightly warmer, or if dark energy had a different strength? We can rewind the tape of cosmic history and watch exactly how a particular galaxy cluster assembled itself, tracing the merger history of its hundreds of constituent galaxies. Researchers like Springel often emphasize that these simulations are not just fancy animations. They are numerical experiments that test the physical laws we believe govern the cosmos. When the simulation produces something that looks like the real universe, it boosts our confidence in the underlying theory. When it doesn't, it tells us our understanding is incomplete and guides us toward what might be missing. This digital journey is now an indispensable partner to telescopic observation. While our telescopes give us a snapshot of the universe at a single moment in time, our simulations show us the movie, revealing the dynamic, evolving story of how it all came to be. They enrich our understanding by allowing us to see the processes that are hidden from our direct view, turning the static map of the cosmic web into a living, breathing narrative of construction and evolution. Yet for all its power as a cosmic architect, gravity is not the only force shaping the destiny of the universe. There is another, far more mysterious player in the game, a force that operates on the grandest scales and works in direct opposition to gravity's relentless pull. This enigmatic presence is known as dark energy, and its discovery not only rewrote the textbooks of cosmology, but also introduced a profound and ironic tension into our understanding of the cosmic web. Just as we are beginning to map the magnificent, gravity-built structures of the universe, we are simultaneously learning that the universe itself is engaged in a project of cosmic dissolution, accelerating their eventual drift into isolation. Dark energy is the name we give to whatever is causing the expansion of the universe to speed up. This is a deeply counterintuitive concept. Imagine tossing a ball into the air, expecting it to slow down and fall back to Earth due to gravity, but instead watching it shoot away from you faster and faster into the sky. That is precisely what astronomers observed happening to the entire cosmos. For most of the 20th century, the prevailing assumption was that the expansion of the universe, initiated by the Big Bang, must be slowing down over time because of the gravitational attraction of all the matter within it. The big question was whether that deceleration would be enough to eventually halt the expansion and lead to a big crunch, or if the universe would simply coast onward forever, expanding at an ever-slowing rate. The shocking answer, discovered in the late 1990s, was that neither of these scenarios was correct. The expansion isn't slowing down at all, it is accelerating. This monumental discovery was made by two independent teams of astronomers who were using distant supernova as cosmic mile markers. A specific type of supernova, known as a type Ia, has a very predictable intrinsic brightness. By measuring how bright these standard candles appear to us here on Earth, astronomers can calculate their distance with great accuracy. Furthermore, by analyzing the redshift of their light, they can determine how much the universe has stretched since the light was emitted. The teams, led by Saul Perlmutter and separately by Brian Schmidt and Adam Rees, expected to find that the more distant supernova, those whose light has been traveling for billions of years, would show that the universe was expanding faster in the past than it is now, evidence of the expected deceleration. Instead, they found the exact opposite. The distant supernova were dimmer than they should have been, meaning they were farther away than their redshifts indicated. The only possible explanation was that the universe had expanded more than expected in the time the light was traveling, meaning the expansion rate has been increasing over time. Something was forcing the galaxies to fly apart from each other at an ever-increasing velocity. For this revolutionary discovery, which fundamentally altered our conception of cosmic destiny, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. The implications of this accelerated expansion for the cosmic web are both profound and deeply ironic. For billions of years, gravity has been the dominant force, tirelessly working to pull matter together to build the great walls, filaments, and clusters. Dark energy, with its repulsive effect, acts as a counterforce to this cosmic construction project. On the scale of individual galaxies and even galaxy clusters, gravity still holds sway. Its pull is strong enough to keep these structures bound together against the overall expansion. But on the very largest scales, the scales of the superclusters and the vast empty voids between them, dark energy is beginning to win. It is not tearing existing structures apart, but it is effectively putting a ceiling on how large they can grow. It is becoming increasingly difficult for gravity to pull together new material from across these ever-widening gulfs of space. The raw building blocks for future giant structures are being swept away from each other faster and faster, isolating the existing nodes of the web. This creates a bizarre and almost poetic cosmic narrative. As Adam Rees has often reflected, we are living in a uniquely privileged moment in cosmic history, a Goldilocks era for cosmology. It is only now that the universe has grown transparent and quiet enough for us to see the large-scale structure clearly. The early universe was a hot, opaque fog, and the far future universe will be so expanded that many galaxies will have been pushed beyond our observable horizon. We exist at just the right time to be able to observe both the detailed structure that gravity has built and the mysterious force that is now beginning to dismantle its work on the largest scales. We are like archaeologists who have just unearthed a magnificent ancient city, only to watch the ocean tides begin to rise and slowly claim the ruins. This tension between the relentless pull of gravity that built the cosmic web and the repulsive push of dark energy that is now stretching it thin is the central drama of modern cosmology, a puzzle that forces us to confront the ultimate fate of everything. While dark energy works to stretch the fabric of spacetime on the grandest scales, and dark matter provides the invisible scaffolding, it is at the specific, dense intersections of the cosmic web where the universe's most spectacular cities of light are built. These are the galaxy clusters, the true metropolises of the cosmos and the most massive structures in the universe that are held together by their own gravity. If the cosmic web is a vast, continent-spanning network of highways and country roads, then galaxy clusters are the brilliant, bustling megalopolises where all those roads meet. A single galaxy cluster is a staggering concentration of matter. It is a gravitational family of hundreds, sometimes even thousands, of individual galaxies, all swarming around a common center of mass. Our own Milky Way is part of a much smaller gathering called the Local Group, which contains about 50 galaxies. A true cluster, like the famous Coma cluster located about 320 million light-years away, is a different beast entirely. It is home to over 1,000 identified galaxies, all bound in a frenetic dance within a region of space roughly 10 million light-years across. The sheer number of stars in such a cluster is a number so large it borders on the meaningless. It is a vault of suns so numerous that counting them is an impossible task. But the galaxies themselves, as brilliant as they are only the most visible part of the story. They are merely the skyscrapers of this cosmic city. The true bulk of a cluster's mass, about 90% of it, is completely invisible. It is the immense halo of dark matter, whose gravitational pull is the only thing powerful enough to hold such a vast structure together. Without this unseen anchor, the galaxies would simply fly apart into the void, their orbital velocities far too great to be contained by the gravity of the visible stars alone. This dark matter forms the fundamental gravitational bedrock of the entire cluster. Then there is the intracluster medium, a phrase that describes the vast ocean of superheated gas that fills the space between the galaxies. This is not a thin, wispy vacuum. It is a searingly hot plasma, heated to temperatures of tens of millions of degrees, so hot that it glows not in visible light, but in high-energy X-rays. This gas is actually the dominant form of ordinary matter in the cluster, containing more mass than all the stars in all the cluster's galaxies combined. It is the leftover primordial fuel from the early universe, the baryonic matter that was drawn into the cluster's immense gravitational well, but was too energetic to collapse and form stars. Studying this hot gas with space-based X-ray telescopes like Chandra gives astronomers a direct window into the cluster's violent history and its total mass. The pressure and heat of the gas act like a probe, allowing scientists to map the depth of the gravitational well it's trapped in, which in turn reveals the amount of dark matter present. This makes galaxy clusters unparalleled natural laboratories for testing the laws of physics under the most extreme conditions. For instance, when two clusters collide in a monumental event that unfolds over hundreds of millions of years, they provide some of the most compelling evidence for the existence of dark matter. The most famous example of this is the Bullet Cluster. During this collision, the two clouds of hot gas from each cluster slammed into each other, slowing down and heating up even further. However, the dark matter from each cluster, which does not interact with anything except through gravity, passed right through the collision unscathed. By mapping the mass distribution using gravitational lensing where the cluster's gravity bends the light from more distant galaxies, astronomers could see that the center of mass of the entire system was not with the glowing gas, but was located where the dark matter had traveled. It was a direct, observational proof that most of the matter is indeed dark and collisionless. Beyond dark matter, clusters also serve as testing grounds for other elusive particles. The same hot, dense intracluster gas should, in theory, be a source of neutrinos, ghostly particles that rarely interact with normal matter. Detecting a flux of neutrinos from a nearby cluster would provide invaluable information about the conditions within that searing plasma and the properties of the neutrinos themselves. Furthermore, the way galaxies move within a cluster provides a precise test of gravitational theories. Their orbits must conform to the shape of the cluster's gravitational field, offering a real-world check on our understanding of gravity itself, on scales far larger than anything we can test in a laboratory on Earth. From our local Virgo cluster, a relative neighbor at 54 million light-years away that serves as the gravitational heart of our own supercluster, to the distant and massive Coma cluster, these cosmic anchors are more than just beautiful collections of galaxies. They are the fundamental nodes where the filaments of the dark matter web converge, the grand crossroads of the cosmos. By dissecting their composition and understanding their dynamics, we are not just cataloging distant wonders, we are conducting fundamental physics experiments on a galactic scale, using the universe itself as our laboratory. While the galaxy clusters are the brilliant, dazzling cities of the cosmos, they are not isolated islands. They are connected, supplied, and defined by an intricate network of cosmic highways that form the very fabric of the web itself. These are the filaments, the great threads of dark matter, gas, and galaxies that stitch the universe together across hundreds of millions of light-years, acting as the vital connective tissue that breathes life into the largest structures we know. To truly appreciate a filament, we must shift our perspective once more. If a galaxy cluster is a sprawling metropolis, then a filament is the vast, continent-spanning river system that feeds it. Picture the Amazon River, but on a scale where the river is 1,000,000 light-years wide, and the water it carries is a faint, diffuse flow of hydrogen gas and dark matter, all streaming relentlessly toward the gravitational pull of the waiting cluster. This is not a passive structure, it is a dynamic conduit, a one-way street guiding the raw building blocks of the universe from the barren hinterlands of the cosmic voids directly into the vibrant hubs of galactic activity. The galaxies within these filaments are like towns and cities built along a riverbank, their growth and evolution shaped by the constant flow of resources passing by. For a long time, these filaments were purely theoretical, the necessary connecting lines in the artist's conception of the cosmic web. But thanks to monumental surveys like the Sloan Digital Sky Survey (SDSS) and the all-sky precision of the Planck satellite, we have moved from theory to direct observation. The SDSS provided the incredibly detailed three-dimensional map, the precise locations of millions of galaxies that trace out the faint outline of these colossal threads. But seeing the galaxies is like seeing the lights of ships sailing on a dark ocean. It shows you the path, but not the water itself. This is where Planck's contribution was revolutionary. By mapping the subtle distortions in the cosmic microwave background caused by the gravitational pull of all the matter, both light and dark in these filaments, Planck effectively allowed us to weigh them. It confirmed that these are not just lines of galaxies, they are massive concentrations of dark matter, the true gravitational backbone of the web, with the galaxies merely being the visible markers along their spine. This constant flow of matter along the filaments has a profound influence on the life cycle of the galaxies within them. A galaxy residing in the heart of a dense cluster lives a violent, tumultuous life, frequently interacting and merging with its neighbors. But a galaxy living out in a filament experiences a very different existence. Research has shown that these filament galaxies are often in a state of transition. They are like commuters who have left the quiet suburbs of the void, but have not yet reached the bustling downtown of the cluster. As they ride this cosmic current inward, they experience a steady increase in encounters with other galaxies and a gradual rise in the density of the intergalactic gas surrounding them. This can trigger bursts of star formation, effectively feeding the galaxy before it eventually reaches the cluster environment, where the harsh conditions might quench its star-forming fuel. The filament is not just a road, it is a preparatory zone, shaping the properties of galaxies long before they arrive at their final destination. The difference between a galaxy living in a filament and one stranded in a void could not be more stark. A void galaxy is an isolated hermit, cut off from the flows of fresh gas and the stimulating interactions with neighbors. It often consumes its available fuel quickly and then fades, a quiet and unevolved relic. A filament galaxy, by contrast, is connected to the cosmic mainstream. It is part of a vast, flowing network, its evolution dictated by its position within this grand circulatory system. This dichotomy emphasizes a critical point that redefines our understanding of the universe. It is not a random scattering of isolated points. It is a complex, interconnected network of relationships, a cosmic ecosystem where a galaxy's fate is determined not just by its own mass, but by its address within the largest architectural structure in existence. The filaments are the great organizers, the channels that dictate the flow of matter and the rhythm of galactic life across the entire observable cosmos. So after exploring these cosmic leviathans from a distance, let's bring the journey home to our own address within this grand cosmic web. For most of human history, our cosmic neighborhood was defined by the stars we could see, then by our galaxy, the Milky Way. But a revolutionary discovery in 2014 completely redefined our local geography, placing us within a structure of such immense scale that it fundamentally reshaped our understanding of where we live. This structure is the Laniakea Supercluster, and its name, from the Hawaiian words for immeasurable heaven, perfectly captures its breathtaking scope. What makes Laniakea so special is that it isn't defined by a simple, static collection of galaxies. Earlier attempts to map our local universe relied on plotting positions, creating a three-dimensional snapshot that suggested we were part of a smaller structure called the Virgo Supercluster. But a team of astronomers led by R. Brent Tully at the University of Hawaii took a far more dynamic approach. They realized that to understand the true architecture of our cosmic region, they needed to map not just where galaxies are, but how they are moving. Think of it like this: if you looked at a map of towns along a river, you might see them as separate points. But if you could see the river itself flowing, you would instantly understand that all those towns are connected by a single, powerful current. Tully's team set out to map the cosmic rivers of gravity. They achieved this by meticulously measuring the peculiar velocities of thousands of galaxies. A galaxy's overall motion is a combination of the general expansion of the universe, which carries everything away from everything else, and a peculiar velocity, its own unique motion through space. This peculiar velocity is caused by the gravitational tug of nearby massive structures. By subtracting the smooth expansion, astronomers can isolate this gravitational motion, effectively mapping the flow patterns of galaxies as they are pulled by unseen masses. When Tully and his colleagues did this for our region of the universe, a stunning pattern emerged. They weren't just seeing random motions, they were witnessing a vast, coherent flow. All the galaxies in our vicinity, including our own Milky Way, are being pulled in a common direction, like leaves caught in a gentle but immense cosmic current. This gravitational watershed revealed the true extent of our home supercluster. Laniakea spans a staggering 520 million light-years and contains the mass of over 100,000 galaxies. Its heart is not a single point but a gravitational basin, a region nicknamed the Great Attractor, toward which everything within Laniakea is slowly, inevitably drifting. Our previous home, the Virgo Supercluster, was demoted to a mere appendage, a branch of this much larger structure. Laniakea's components read like a cosmic roll call of our most prominent neighbors. It encompasses the massive Virgo cluster, which acts as a local gravitational anchor, as well as the Hydra Centaurus Supercluster, a major concentration of galaxies lying in the direction of the Great Attractor. Even our own local group of galaxies, with Andromeda and the Milky Way, is just a tiny suburb on the outskirts of this immense metropolitan expanse. The discovery of Laniakea is a profound lesson in cosmic humility and perspective. For centuries, we looked at the night sky and saw ourselves at the center of everything. First, we were the center of the solar system, then the center of the galaxy. Now we understand that our entire galaxy is just one of 100,000, flowing along a gravitational highway toward a destination we cannot yet fully see. It personalizes the vast, abstract concept of the cosmic web. We are not just observers of this grand design, we are participants within it, carried along by the same fundamental forces that govern the universe's largest structures. Knowing we live in Laniakea transforms our place in the cosmos from a static point on a map to a dynamic journey within an immeasurable heaven, making the mind-boggling scale of the universe suddenly, intimately relatable. But this grand, flowing journey within Laniakea is not aimless. It is a directed voyage toward a specific, and for a long time, deeply mysterious destination. For decades, astronomers have known that our Milky Way and its neighbors are not just drifting apart with the universe's expansion. They share a common, peculiar velocity, a distinct trajectory through the cosmos. We are all moving toward a specific point in the sky, pulled by the gravitational influence of something immense and hidden. This unseen master of our local cosmic flow is known as the Great Attractor, and its story is a perfect example of how some of the most profound discoveries are hidden literally in our own backyard, obscured by the very galaxy we call home. The first clues to this mystery emerged from studies of the cosmic microwave background. This primordial radiation creates a universal frame of reference. As our solar system moves through space, we experience a slight Doppler shift in this background glow. It appears slightly warmer in the direction we're heading and slightly cooler behind us. By carefully mapping this dipole anisotropy, scientists could determine our motion relative to the rest frame of the universe. The result was startling. Our entire local group of galaxies, along with thousands of others, is hurtling through space at an astonishing velocity of over 600 kilometers per second. That's well over 1 million miles per hour, and this motion is not random. It is aimed precisely toward a region in the southern sky, centered on the constellations of Centaurus and Norma. This presented an immediate and frustrating puzzle. When astronomers pointed their optical telescopes toward that part of the sky to see what was pulling us, they were met with a wall of darkness. This is because that direction lies directly along the plane of our own Milky Way galaxy, a region brimming with gas, dust, and countless stars. This is the zone of avoidance, a swath of the sky where the dusty disk of our galaxy blocks our view of the distant universe, creating a blind spot in our cosmic vision. For years, the Great Attractor remained exactly that, a gravitational signature without a visible source, a classic scientific enigma. What colossal mass could possibly be exerting such a powerful pull, and why couldn't we see it? The breakthrough came when astronomers switched their tools, moving from visible light to wavelengths that can pierce the galactic veil. Radio and infrared telescopes became the keys to unlocking this mystery. Pioneering work using the Parkes Observatory radio telescope in Australia began to map the distribution of hydrogen gas in galaxies hidden behind the Milky Way's dust. By detecting the radio waves emitted by this neutral hydrogen, astronomers could effectively see through the obscuration, pinpointing the locations and velocities of galaxies that were completely invisible to optical surveys. What they revealed was a staggering concentration of mass. The Great Attractor was not a single, monolithic object, but rather a massive gravitational overdensity, a focal point where the filamentary flows of the cosmic web converge. This hidden region appears to be the core of our local supercluster, Laniakea, and is dominated by a massive cluster of galaxies known as the Norma cluster. While not the largest cluster known, its location at the heart of this immense gravitational watershed gives it an outsized influence. It acts as the central anchor, the gravitational nucleus of the entire Laniakea Supercluster. But the Norma cluster alone did not fully account for the observed pull. Further observations, particularly in the infrared by missions like the Infrared Astronomical Satellite and the 2-micron all-sky survey, continued to unveil more hidden galaxies, painting a picture of an even larger complex of mass now known as the Norma Supercluster. This entire conglomerate, a dense knot in the cosmic web where multiple filaments meet, is the true engine of the Great Attractor. The fascination with this gravitational anomaly lies in its powerful lesson about the limits of our perception and the nature of scientific discovery. Here was a force literally shaping the motion of our entire galaxy, a fundamental driver of our journey through the cosmos, and it was hidden from view by a relatively thin layer of local dust. It proved that even in our own cosmic neighborhood, there were profound secrets waiting to be uncovered, reminding scientists that the most important discoveries aren't always at the edge of the observable universe. Sometimes they are hidden in plain sight, just behind a dusty curtain. The quest to map the Great Attractor exemplifies the relentless drive of astronomy to peer beyond obscuration, to use every tool at our disposal to illuminate the dark and understand the hidden forces that govern the architecture of the universe. It stands as a thrilling reminder that the cosmic web is not just a map of distant giants. Its invisible threads are tugging on us right now, guiding our path through the immensity of space. And so the mystery of the Great Attractor presented astronomers with a classic cosmic detective story, one where the culprit's gravitational signature was clear, but the suspect remained hidden from view. The reason for this frustrating obscurity lies in a fundamental and long-standing challenge for astronomers: the zone of avoidance. This is not some mystical barrier or a region of empty space. It is a very real and physical obstacle created by our own cosmic address. Imagine trying to map a distant mountain range but a vast nearby forest of your own making. A forest with incredibly dense, dusty trees blocks your entire view of what lies beyond. That forest is the plane of our Milky Way galaxy, and the zone of avoidance is the swath of the sky where its thick clouds of gas and dust, along with countless stars, completely obscure our vision of the extragalactic universe behind it. For centuries, this zone represented a massive blind spot on our cosmic maps, a blank space covering about 20% of the entire sky. Optical telescopes were rendered nearly useless here. The visible light from distant galaxies is easily absorbed and scattered by the Milky Way's interstellar dust, preventing it from ever reaching our eyes or instruments. It was as if we were trying to study the world outside our house by looking through a window that had been completely painted over. This obscuration meant that any large-scale structures lying directly behind this zone, including the crucial region toward which we are streaming, remained a complete and utter mystery. The Great Attractor's pull was undeniable, but its face was hidden, a gravitational ghost haunting the edges of our perception. The key to piercing this veil was a fundamental shift in strategy. If we cannot see through the dust with our eyes, we must learn to see with other senses. Astronomers turn to the parts of the electromagnetic spectrum that can travel through the galactic murk unimpeded. Just as certain sounds can travel through walls that block light, radio waves and infrared radiation have the unique ability to pass through the Milky Way's dust clouds with relative ease. This required a new generation of eyes on the sky. Radio telescopes, like the iconic Parkes Observatory in Australia with its massive 64-meter dish, became vital explorers of this hidden realm. By tuning into the specific radio wavelength of 21 centimeters, the signal emitted by neutral hydrogen gas, astronomers could detect the presence of galaxies hidden behind the dust. Every spiral galaxy contains vast reservoirs of this gas, so by mapping the distribution and velocity of this hydrogen, researchers could effectively chart the structures lurking in the zone of avoidance without ever seeing their stars. Infrared astronomy provided the other crucial window. Infrared light, with its longer wavelengths compared to visible light, is far less susceptible to scattering by dust particles. Space-based infrared observatories, free from the absorbing effects of Earth's atmosphere, became our scouts into the unknown. Missions like the Infrared Astronomical Satellite in the 1980s, and later the magnificent 2-micron All-Sky Survey, peered through the galactic fog, not by looking through it with visible light, but by sensing the heat signature of the stars themselves. They revealed thousands of previously hidden galaxies, their starlight redshifted into the infrared by the intervening dust, finally making the invisible visible. The result of this multi-wavelength crusade was a revelation that completed our map of the local cosmos. It was the astronomical equivalent of the moment ancient mapmakers finally sailed around a forbidding cape to discover the lands beyond. The careful, patient work of radio and infrared astronomers unveiled the full extent of the mass concentration pulling us toward the great attractor. They confirmed the Norma cluster as a major anchor point, but also revealed that it was merely the brightest node in a much larger and more massive complex, now known as the Norma Supercluster. This entire region is a dense knot in the cosmic web, a grand central station where the gravitational filaments of Laniakea converge. The motion of our galaxy was no longer a mystery. We were simply riding the gravitational current down into this immense valley of space, a small boat on a vast cosmic river whose source was now finally revealed. Astronomers often compare this decades-long effort to the exploration of a hidden continent. For generations, we knew the continent was there. We could feel its gravitational pull on our ships, but we had no maps of its coastline or its interior. Each new survey, each technological advancement in radio receivers or infrared detectors, was like sending out another expedition to chart another river or mountain range. The perseverance required was immense, demanding collaboration across observatories and continents, all focused on illuminating a single, stubbornly dark patch of sky. Overcoming the obstacle of the zone of avoidance is more than just a technical achievement. It is a powerful symbol of the entire scientific endeavor. It embodies the relentless human drive to see beyond our immediate limitations, to use ingenuity and technology to reveal truths that nature has seemingly hidden from us. It is a profound testament to the idea that the universe is knowable, even when it deliberately obscures its own wonders, and that every blank space on a map is not an end, but an invitation to explore. This grand cosmic web we've been exploring, with its magnificent walls and vast voids, did not simply spring into existence fully formed. It has a biography, a dynamic life story that unfolds across nearly the entire age of the universe. To truly appreciate its present-day majesty, we must rewind the cosmic clock and witness its evolution from the faintest of whispers to the Leviathan we see today, a process driven by gravity's relentless patience and shaped by the universe's expanding stage. Our story begins, as all modern cosmic histories do, with a cosmic microwave background. Those tiny temperature fluctuations, those faint ripples of slightly denser and slightly emptier space, are the opening chapter. They are the primordial seeds from which everything would grow. For the first several 100 million years, the universe was too hot, too smooth, and expanding too rapidly for these seeds to do much of anything. The slight overdensities had a tiny gravitational advantage, but the outward pressure of radiation and the overall expansion of space acted as a powerful brake, suppressing any significant growth. It was a cosmic stalemate, a period known as the Cosmic Dark Ages, where the universe was a vast, featureless, and dark expanse of cooling gas. The turning point arrived with the formation of the first stars and galaxies, an era romantically dubbed Cosmic Dawn. As the first massive stars ignited, their intense ultraviolet radiation began to reionize the neutral hydrogen gas that filled the universe, burning away the fog and making space transparent once more. But more importantly for our story of structure, the gravitational landscape was finally ready to change. Dark matter, which had been quietly clumping together unimpeded by radiation pressure, had already laid down a faint, invisible scaffolding. Now, ordinary matter, the gas could finally respond to gravity's call. It began to flow into the gravitational wells of the dark matter halos, collapsing to form the first proto-galaxies. This was the end of the universe's smooth, featureless adolescence and the beginning of its journey toward complexity. From this point onward, the dominant theme of the cosmic web's evolution is hierarchical structure formation. This is an elegant term for a simple idea. Small things merge to form bigger things. The first structures to form were tiny, small protogalaxies, perhaps the size of a dwarf galaxy. Gravity then began to orchestrate a grand, billion-year dance of attraction and merger. These small galaxies, drawn together by their mutual gravity, collided and merged to form larger galaxies. Groups of these larger galaxies then found each other, drawn along the filaments of the dark matter web, and merged to form galaxy clusters. The clusters themselves, at the intersections of multiple filaments, continued to accrete more galaxies and even entire groups, growing ever more massive. It is a bottom-up process, a cosmic form of assembly where the universe builds its largest structures by piecing together smaller prefabricated units. This hierarchical growth is the reason why the largest galaxy clusters, the most massive cities in the cosmos, are always found at the nodes where the thickest filaments of the web intersect. They are the ultimate destinations for all the matter flowing along the cosmic highways. We are not left to simply theorize about this ancient history. We have a powerful time machine that allows us to witness it directly, the Hubble Space Telescope. By staring for days at a single, seemingly empty patch of sky to create the Hubble Ultra-Deep Field, Hubble did something revolutionary. It gathered the faint light that had been traveling for over 13 billion years, allowing us to see galaxies not as they are today, but as they were in the distant past. The image that resulted is not just beautiful, it is one of the most profound documents in all of science. It shows us a universe in its youth, a chaotic and crowded place teeming with small, irregular, and fiercely active protogalaxies. These are not the grand, well-ordered spirals and ellipticals we see in our local universe. They are the building blocks, the small units that hierarchical growth predicts. We see them in the process of merging, their shapes distorted by violent interactions, their cores blazing with the light of frantic star formation. The ultra-deep field is a snapshot of the cosmic web under construction, a direct visual confirmation that the universe looked profoundly different in the past, and that the serene architecture we see today was forged in a fiery epoch of constant collision and assembly. So what does the future hold for this ever-evolving web? Our current models, refined by both observation and simulation, paint a fascinating and ultimately lonely picture. For the next several tens of billions of years, gravity will continue to do its work, albeit with an increasingly powerful opponent. The process of hierarchical growth will continue. Filaments will thicken as more matter streams into them. Galaxy clusters will grow ever larger and more massive as they continue to cannibalize smaller groups and accrete galaxies from the filaments that feed them. Our own local group is a participant in this future. The Milky Way and the Andromeda Galaxy are destined to merge in about 4 billion years, eventually forming a new, larger elliptical galaxy that astronomers have nicknamed Milkomda. On larger scales, our entire Laniakea Supercluster will likely coalesce into a single, massive cluster of galaxies. However, this era of construction is ultimately finite. The accelerating expansion of the universe, driven by dark energy, is already putting a ceiling on the future growth of the cosmic web. While gravity dominates locally, binding galaxies and clusters together, dark energy dominates globally. As the expansion accelerates, the vast empty voids between the superclusters will stretch at an ever-increasing rate. The cosmic rivers that currently feed the clusters will eventually run dry. The raw material for future growth, lonely galaxies and dwarf groups stranded in the expanding voids, will be swept away by the accelerating fabric of space, becoming forever isolated and unreachable. New matter will be unable to flow into the existing web, effectively freezing the large-scale structure in place. The universe will become a place of isolated island universes, the massive, merged galaxy clusters separated by ever-widening gulfs of truly empty space, their light slowly fading as star formation ceases and their stars burn out. This historical perspective, from quantum seed to mature web to frozen architecture, enriches our appreciation for the cosmic web not as a static painting, but as a dynamic, evolving entity. We are living in a special time, a golden age for cosmology, where the universe is still transparent enough to see its structure, and the lights are still on in its grandest cities, allowing us to witness this magnificent act of cosmic construction while the show is still playing. Yet, just as we begin to map the grand architecture of the cosmic web, a discovery emerges from the data so immense, so seemingly impossible, that it threatens to unravel our entire understanding of the universe's scale and structure. This is the story of the Huge Large Quasar Group, or HLQG, a formation so colossal that its very existence appears to break the fundamental rules of cosmology. To grasp its scale, we must first understand what a quasar truly is. In the 1960s, astronomers began detecting incredibly bright, point-like radio sources that seemed to defy classification. They looked like stars, but their spectra were unlike anything seen before. We now know these quasi-stellar objects, or quasars, are not stars at all. They are the intensely luminous cores of distant galaxies, powered by supermassive black holes in a state of incredible feasting. As vast amounts of gas and dust spiral inward toward the black hole, they form a superheated accretion disk that can outshine the entire surrounding galaxy, making quasars the brightest beacons in the universe, visible from billions of light-years away. Because quasars are associated with the most massive galaxies, which in turn form in the densest knots of the dark matter web, they serve as perfect tracers for the underlying large-scale structure of the universe. Where you find a concentration of quasars, you are effectively mapping a concentration of immense mass. It was precisely this mapping exercise that led a team of astronomers, led by Roger Clowes of the University of Central Lancashire, to make their staggering discovery. By meticulously analyzing data from the Sloan Digital Sky Survey, they identified a group of 73 quasars that appeared to be gravitationally linked, forming a structure that stretched across an almost incomprehensible 4 billion light-years at its widest point. To put that into a human perspective, if you could somehow travel at the speed of light, it would take you nearly twice the current age of our entire solar system just to cross from one end of this group to the other. This was not merely a larger version of the Sloan Great Wall. It was an object from an entirely different category of immensity. The discovery sent immediate shockwaves through the cosmological community because its scale directly challenges one of the most sacred principles in all of astronomy, the cosmological principle. This foundational idea states that on sufficiently large scales, the universe should appear homogeneous and isotropic, meaning it should look roughly the same in every direction and from every location. There should be no preferred center and no discernible edge. This principle is not just philosophical, it is the bedrock upon which Einstein's equations and our entire model of the universe are built. The theoretical limit for such homogeneity, based on our standard lambda cold dark matter model, is around 1.2 billion light-years. The Huge Large Quasar Group, at nearly 4 times that size, doesn't just nudge against this limit, it crashes through it with staggering force. Its existence suggests that the universe might be lumpy on scales we never thought possible, implying that matter is not evenly distributed but instead clumped together in a way that our current physics cannot easily explain. Roger Clouse and his colleagues were understandably cautious, acknowledging that such an extraordinary claim requires extraordinary evidence. They employed rigorous statistical analysis to show that the probability of these 73 quasars aligning by pure chance was vanishingly small. As Clouse himself stated, the structure is so significant that it challenges the assumption of the cosmological principle. The immediate reaction from many cosmologists was one of healthy skepticism. Could this be a chance alignment, a statistical fluke known as a projection effect, where multiple smaller structures at different distances simply appear connected from our particular vantage point? Others questioned whether our methods for estimating the distances to these quasars could be introducing a systematic error, making the group appear more connected than it truly is. The debate is a perfect and beautiful example of the scientific process in action, where a single anomalous discovery forces the entire community to re-examine its assumptions and sharpen its tools. But the potential implications are too profound to ignore. If the huge large quasar group is confirmed to be a single, coherent structure, it would force a dramatic revision of our standard model of cosmology. It might suggest that the process of inflation in the early universe, which set the initial conditions for all structure, operated differently than we think, perhaps generating primordial density fluctuations on scales far larger than our models predict. Alternatively, it could point towards something even more radical, like a need to modify our understanding of gravity itself on the largest scales, or perhaps even hint at a more complex topology for the universe than we have ever imagined. This one discovery, this single thread in the cosmic tapestry, has the power to pull at the seams of our entire understanding, demonstrating that our journey to map the cosmos is far from complete. Each new layer we peel back reveals not just answers, but deeper, more fundamental questions, proving that the universe will always have mysteries waiting just beyond the edge of our current knowledge. And just when we thought our local cosmic map was nearly complete, a hidden continent of galaxies was discovered lurking in our own backyard, a structure so immense it had been hiding in plain sight for decades. This is the story of the South Pole Wall, a gravitational behemoth uncovered in 2020 that reminds us there are still colossal secrets waiting to be found, even in the seemingly well-charted territories of our local universe. Stretching over an astonishing 1.4 billion light-years, this vast filamentary structure is a monumental ridge in the cosmic web, a great wall of galaxies and dark matter that ranks as one of the largest contiguous structures ever identified, yet it had remained invisible to us because of a simple cosmic accident of perspective. The challenge in finding the South Pole Wall was not its distance, but its location. It resides in the southern celestial hemisphere, positioned in such a way that a significant portion of it lies directly behind the plane of our own Milky Way galaxy, once again falling victim to that familiar foe, the zone of avoidance. But unlike the Great Attractor, which was detected by its gravitational pull on our motion, the South Pole Wall required an even more sophisticated and indirect form of cosmic cartography to be revealed. The international team of researchers, led by cosmologist Daniel Pommard, employed a brilliant technique that focused not on the positions of galaxies, but on their motions. They meticulously mapped the peculiar velocities of thousands of galaxies, that is, their individual movements through space after subtracting the uniform expansion of the universe. These peculiar velocities are not random. They are the direct fingerprints of gravity caused by the tug of massive structures. By analyzing this flow, astronomers can essentially trace the gravitational landscape, mapping the hills and valleys of the cosmic web by watching how galaxies roll through them. To build this map, the team had to become master data synthesizers, weaving together information from an array of the world's most powerful sky surveys. They integrated galaxy redshift data from the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and the Cosmic Flows database, which is one of the most extensive collections of galaxy distance measurements ever assembled. This was not a discovery made by a single telescope peering into the void. It was the product of a global, collaborative effort in the digital realm, a triumph of big data astronomy. Supercomputers crunched the numbers, processing the observed velocities of over 18,000 galaxies to reconstruct the underlying gravitational field that must be causing them. What emerged from this complex statistical analysis was the ghostly outline of a titan, a vast, arching wall of mass bending through the southern sky like a great cosmic barrier, with one end near the celestial South Pole and the other curving upward, its full extent previously masked by our galactic disk. The significance of the South Pole wall extends far beyond its impressive scale. Its discovery provides a critical missing piece in the puzzle of our local cosmic flows. For years, the motion of our local group of galaxies has been attributed to the combined pull of known structures like the Virgo cluster, the Great Attractor, and the even more massive Shapley Supercluster farther away. The South Pole Wall adds a major new player to this gravitational tug-of-war. Its immense mass, which includes the already known Vela and Puppis clusters now understood to be mere parts of this larger whole, exerts a significant influence on the motion of galaxies in our vicinity, including our own. Its presence helps to refine our models of how dark matter is distributed on the largest scales, offering a new testbed for simulations that seek to understand the precise balance of forces that have shaped our corner of the universe. It proves that our census of the local web is still incomplete, and that even with our advanced technology, we are still capable of overlooking giants that lie just beyond the veil of our own galaxy. This recent finding is a powerful testament to the ingenuity of modern astronomy, demonstrating that by combining different wavelengths of light and innovative analytical techniques, we can continue to uncover hidden realities and scale new cosmic mountains that were hiding in the shadows all along. So here we stand, confronted by these cosmic leviathans, the Hercules corona Borealis Great Wall, the huge large quasar group, structures of such immense scale that they seem to defy the very rules we thought governed the universe. This isn't just a minor discrepancy in the data, it's a direct challenge to one of the most fundamental pillars of modern cosmology, the cosmological principle. This principle is the bedrock assumption that on the largest scales, the universe is homogeneous and isotropic. In simpler terms, it means that no matter where you are or what direction you look, the overall distribution of matter should appear roughly the same. There are no special places, no centers, and no edges. This idea isn't just philosophical. It's the essential foundation that allows us to apply our physical laws uniformly across the cosmos and to use the Big Bang model as a reliable description of reality. When we see a structure that spans a significant fraction of the observable universe, it directly questions that foundational belief, forcing us to ask if our entire understanding is built on shaky ground. The immediate and most conservative explanation from many in the scientific community is that these are not actual physical structures in the way we think of them, but rather statistical flukes or artifacts of how we observe the universe. This is a perfectly reasonable starting point. When you're mapping something as vast as the cosmos, sometimes patterns can emerge simply by chance. Imagine rolling a dice and getting 6 sixes in a row. It's improbable, but not impossible. Some cosmologists argue that these giant formations could be similar, rare but possible alignments of smaller, unrelated structures that just happen to fall along our particular line of sight, creating the illusion of a connected wall or group. This perspective urges caution, demanding more data, better surveys, and more rigorous statistical analysis before we tear down the entire cosmological rulebook. It's the scientific method at its best. Extraordinary claims require extraordinary evidence. Yet, if further observations continue to confirm that these are indeed coherent structures, then we must seriously consider the possibility that our physics is incomplete. This is where the conversation turns from cautious skepticism to thrilling, paradigm-shifting speculation. One compelling avenue is to re-examine our theory of cosmic inflation, that period of furious expansion in the universe's first fraction of a second. Perhaps inflation did not generate perfectly scale invariant fluctuations as we currently believe. Maybe it left behind primordial wrinkles on scales far larger than we anticipated, creating these colossal seeds that gravity then amplified. Another possibility is that we need to modify our understanding of gravity itself. Einstein's theory of general relativity has been spectacularly successful, but it has never been tested on the mind-boggling scales of billion light-year structures. Could it be that gravity behaves differently over these vast distances, allowing matter to clump in ways our current equations don't predict? Theories like modified Newtonian dynamics, or MUND, though controversial, represent this kind of bold thinking. This line of inquiry leads to some of the most profound and imaginative ideas in theoretical physics. Cosmologist Laura Mersini-Horton has proposed a fascinating connection between these massive anomalies and the concept of the multiverse. Her work suggests that the gravitational pull from other universes in a vast multiverse could have left an imprint on our own during inflation, creating these giant patterns in the cosmic microwave background and the large-scale structure that follows. As she has eloquently put it, these structures could be the scars of our universe's birth from the multiverse. This isn't just wild speculation. It's a testable hypothesis that makes specific predictions about where other such anomalies should be found in the sky. It represents a breathtaking synthesis of the largest structures we can observe with the most fundamental questions about the nature of reality itself. This tension between established theory and startling new observation is not a crisis for science, it is its engine. Throughout history, the most significant breakthroughs have come from precisely this kind of anomaly, a measurement that doesn't fit, an observation that contradicts the prevailing wisdom. It is the discomfort of not knowing that propels us forward. The existence of these potential rule breakers doesn't mean our current models are worthless, far from it. The lambda-cold dark matter model remains incredibly successful at explaining a vast array of cosmic phenomena. But these giants remind us that our models are approximations, maps that are useful but never a perfect territory. They are invitations to explore, to dig deeper, and to dream bigger. The most exciting discoveries rarely lie in confirming what we already know, but in grappling with what we don't. These cosmic challenges are not walls blocking our path. They are doorways, and on the other side awaits a deeper, richer, and more astonishing understanding of the universe we call home. But the quest to map the cosmic web doesn't end with photons. For centuries, astronomers have relied solely on light from visible waves to radio and X-rays to unravel the universe's secrets. This is electromagnetic astronomy, and it has given us everything we know. But light, for all its brilliance, can be obscured, distorted, or simply not emitted by the most mysterious components of the cosmos. To truly see the unseen, we must listen to the universe as well as look at it. We are entering a revolutionary new era defined by multi-messenger astronomy, a discipline that expands our senses beyond light to include the whispers of gravitational waves, the ghosts of neutrinos, and the atomic fragments of cosmic rays. This is not just a new tool, It is an entirely new way of perceiving the cosmic web, allowing us to feel its structure through the ripples in space-time and sense its densest environments through particles that pass through planets like they aren't even there. Gravitational waves provide perhaps the most profound new sense, predicted by Einstein a century ago and finally detected in 2015 by the LIGO observatories. These are ripples in the very fabric of spacetime itself, caused by the most violent events in the universe, the mergers of black holes and neutron stars. Think of spacetime as a silent, still pond. When a cataclysmic merger occurs, it's like dropping a heavy rock into that pond, sending out ripples that travel across the entire universe at the speed of light. The beauty of these ripples is that they are completely unaffected by anything they pass through. Dust clouds, magnetic fields, entire galaxies, nothing stops or distorts a gravitational wave. By the time these ripples reach us, incredibly faint after their billion light-year journey, our exquisitely sensitive detectors like LIGO, Virgo, and now CAGRA can measure the minuscule stretching and squeezing of space they cause. So how does this help us map the cosmic web? Every single gravitational wave event comes with a precise distance measurement encoded in its signal. However, pinpointing its exact location on the sky is still a challenge. The wave itself only tells us a general area of origin. This is where the multi-messenger approach becomes essential. If a merger event also produces a flash of light, like the spectacular kilonova that accompanied the neutron star merger observed in 2017, then optical telescopes can swoop in to identify the host galaxy. This gives us a precise three-dimensional coordinate for that event. But even for the many mergers that are dark, statistical cosmology comes into play. By building a vast catalog of these events and their general directions, astronomers can begin to create a three-dimensional map of where these monstrous mergers are happening across the universe. Do they cluster along the predicted filaments of the cosmic web? Do they avoid the vast voids? This data will provide an entirely independent way to trace the large-scale distribution of matter, particularly the elusive neutron stars and black holes that are often invisible to traditional telescopes. Then there are neutrinos, the ultimate cosmic ghosts. These nearly massless particles are produced in abundance in the hearts of stars, during supernova explosions, and around the supermassive black holes at the centers of active galaxies. Their defining characteristic is that they barely interact with anything at all. Trillions of neutrinos from the sun are passing through your body every second, completely unnoticed. This aloof nature is also their greatest strength for astronomy. A neutrino can travel in a perfectly straight line from the most distant and dense environments in the universe, like the heart of a galaxy cluster or the accretion disk of a blazar, directly to our detectors without being deflected or absorbed. They are perfect messengers, carrying uncontaminated information from the most extreme places. Observatories like the Ice Cube Neutrino Observatory at the South Pole are designed to catch these rare, interactive ghosts. Ice Cube consists of a cubic kilometer of pristine Antarctic ice instrumented with thousands of sensitive optical sensors. On the exceedingly rare occasion that a neutrino does collide with an atom in the ice, it creates a faint flash of blue light that the sensors can detect. By analyzing the energy and direction of these events, scientists can trace the neutrino's path back to its source. This is already paying dividends. In 2018, Ice Cube detected a high-energy neutrino and alerted astronomers around the world. They traced it back to a flaring blazar, a galaxy with a supermassive black hole shooting a jet of radiation directly at Earth, billions of light-years away. This was a landmark multi-messenger event, linking a neutrino to a specific source for the first time. For mapping the cosmic web, a steady flow of neutrino data from such extreme environments can tell us about the conditions within the dense nodes of the web. the galaxy clusters and active galactic nuclei. They can reveal how particles are accelerated in these environments and provide a unique probe of the physics at work where the cosmic web's filaments converge. Looking to the future, the potential of these new messengers is boundless. The next generation of gravitational wave observatories, like the space-based LISA mission planned for the 2030s, will be sensitive to the mergers of supermassive black holes, events that can shake the entire fabric of spacetime. Mapping these titanic collisions will directly trace the most massive nodes of the cosmic web across cosmic time. Furthermore, both gravitational waves and neutrinos offer a potential, though highly challenging, path to detecting dark matter itself. Certain theoretical models suggest dark matter particles could accumulate in the cores of stars or could even decay, producing faint neutrino signals or potentially even gravitational waves. While this remains speculative, it represents the cutting edge of the search. These messengers also provide a new way to measure the expansion rate of the universe. A gravitational wave source gives a direct, absolute distance to an event, which can be compared to its redshift to measure the Hubble constant in a way that is completely independent of the traditional cosmic distance ladder, helping to resolve one of the biggest tensions in modern cosmology. This integrated methodology of multi-messenger astronomy is transforming us from passive observers of the cosmic web into active listeners. We are no longer just studying the light from the universe's cities. We are feeling the tremors from its earthquakes and decoding the messages sent by its most reclusive inhabitants. It promises to unveil the dark, hidden dimensions of the cosmic architecture, revealing the full, dynamic picture of how the universe is structured and how it evolves, deepening our journey into the cosmos in ways we are only beginning to imagine. This incredible journey through the cosmic web, from its faint beginnings to its present-day majesty, has been built on decades of painstaking observation and theoretical brilliance. But what if I told you that everything we've discovered so far might just be the opening act? We are standing on the precipice of a new golden age of discovery, an era where our maps of the universe will transition from rough sketches to high-definition blueprints, thanks to a new generation of telescopes and missions so powerful they will redefine the very field of cosmology. The tools that built our current understanding are about to be joined by giants, and their collective gaze will pierce deeper into the dark, revealing the cosmic web in a detail we can now only dream of. Leading this charge from the ground is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, a facility that redefines the very concept of a sky survey. Perched atop a mountain in Chile, its mission is breathtakingly simple and monumentally ambitious: to photograph the entire available sky every few nights for an entire decade. This isn't just taking a few pictures, it's creating a deep, ultra-high-definition movie of the cosmos. At its heart is the largest digital camera ever built for astronomy, a 3.2 billion pixel behemoth that will capture images so vast that it would take over 1,500 high-definition television screens to display just one of them at full size. The volume of data it will produce is almost incomprehensible. It is expected to catalog over 20 billion galaxies and a similar number of stars, measuring the shape, distance, and brightness of each one. For the cosmic web, this relentless scanning is the key to unlocking its dynamics. By tracking subtle changes over time and mapping the precise positions and shapes of billions of galaxies, Rubin will trace the dark matter filaments that connect them with unparalleled clarity, potentially even spotting the subtle distortions caused by the cosmic web's faintest tendrils. It will provide the most comprehensive census of our universe ever conducted, a dataset that will undoubtedly contain anomalies and surprises that will keep astronomers busy for the next 50 years. While Rubin scans from the ground, the Euclid space mission is performing a complementary and equally revolutionary survey from the pristine darkness of space. Launched by the European Space Agency, Euclid is a dedicated cosmology machine designed to answer one overarching question: what is the nature of dark energy and dark matter? It will do this by mapping the geometry of the universe itself. Free from the distorting effects of Earth's atmosphere, Euclid's sharp eyes will measure the shapes of over 1 billion galaxies with exquisite precision, using a technique called weak gravitational lensing. As the light from these distant galaxies travels toward us, it is subtly bent by the gravitational pull of all the matter, both light and dark, in its path. By analyzing these tiny distortions en masse, Euclid will create a three-dimensional mass map of the universe, effectively showing us where all the dark matter is. Simultaneously, it will use another method, measuring the clustering of galaxies across 10 billion years of cosmic history. By observing how the large-scale structure has grown over time, scientists can precisely measure the influence of dark energy, which works to suppress this growth. The combination of these two powerful probes will allow Euclid to test whether dark energy is truly a constant force or something that varies over time, a question that gets to the very heart of the universe's ultimate fate. Then there is the project that truly embodies international ambition and sheer scale, the Square Kilometre Array, or SCAR. This isn't a single telescope but a vast network of them, with thousands of antenna dishes and up to 1 million low-frequency antennas spread across South Africa and Australia. As the name suggests, its total collecting area will eventually be about 1 square kilometer, making it the most sensitive radio observatory ever constructed. The SKA will peer into the cosmic dawn, detecting the faint radio signals from neutral hydrogen gas in the very first galaxies to form after the Big Bang. This ability to map the distribution of hydrogen across cosmic time is like having a time-lapse video of the cosmic web's construction from its very foundations. It will trace how gas flows into the dark matter filaments and feeds the growing galaxies at their nodes, directly observing the processes we currently only simulate on supercomputers. Its sensitivity is so great that it could potentially detect the faint emission from hydrogen gas within the cosmic web filaments themselves, moving from inferring their presence through galaxies to directly imaging the raw material flowing through them. Furthermore, by surveying billions of galaxies through their hydrogen signature, the SKA will create its own enormous map of the universe's structure, providing an independent and powerful check on the optical surveys of Rubin and Euclid. The collective excitement within the global astronomical community for these projects is palpable, a feeling of standing on the edge of a new frontier. They are not just incremental improvements, they are quantum leaps in capability. Wendy Friedman, a renowned cosmologist involved in planning for these next-generation surveys, has spoken about the profound shift they represent, moving from studying thousands of galaxies to studying billions, a change that will allow us to see the statistical forest rather than just individual trees. This leap in data quality and quantity is what gives scientists the confidence that they will finally be able to resolve the nagging mysteries we've been discussing. The true scale of the largest structures, like the Hercules Corona Borealis Great Wall, will be put to the test. With billions of precise distance measurements, we will know definitively whether these are coherent physical structures or chance alignments. The tension between different measurements of the universe's expansion rate, a current crisis in cosmology, might finally be broken by the sheer weight of new, precise data from multiple independent methods. We might even find that the cosmic web holds clues to the nature of dark matter itself, perhaps revealing subtle differences in how it clumps that could point toward specific particle properties. The most thrilling prospect is the certainty of the unknown. Every time humanity has built a new telescope with a significantly new capability, it has made discoveries we never predicted. The Vera C. Rubin Observatory, with its nightly scan of the entire sky, is almost guaranteed to uncover new classes of transient objects, explosions, or events that flare up and fade away quickly that we didn't know existed. Euclid's deep, wide field view could reveal unexpected large-scale asymmetries in the universe that challenge the cosmological principle in a new way. The scar, listening to the faint whispers from the universe's infancy, could detect a signal that completely rewrites our story of how the first stars and galaxies formed. These telescopes are not just tools for answering our current questions. They are engines for generating new, more profound questions we haven't even thought to ask yet. Within the next decade, the data flowing from these observatories will transform our understanding of cosmic architecture from a sketch into a living, breathing, and dynamic map, inspiring a new generation to look up and wonder what else is waiting to be found. But how do we move from simply observing this magnificent structure to truly understanding its history? How do we trace the evolution of the cosmic web back through billions of years to its very origins? This is the domain of a fascinating and deeply clever field known as cosmic archaeology. Just as a geologist can examine the layers of rock in a canyon wall to deduce the sequence of earthquakes and floods that shaped a landscape, cosmic archaeologists scrutinize the present-day arrangement of galaxies to uncover the ancient events that built the universe we see today. It is a form of detective work on the grandest possible scale, where the clues are written in the motions of stars, the chemical fingerprints of ancient suns, and the ghostly remnants of long-dead galaxies. One of the most powerful techniques in this cosmic detective's toolkit is the study of relic stellar populations. Throughout a galaxy's long life, it undergoes countless changes, but its oldest stars serve as living fossils, preserving a pristine record of the conditions in which they formed. These ancient suns, often found in vast halos surrounding galaxies or in dense clusters known as globular clusters, are like time capsules. They formed from the primordial gas of the early universe, gas that had been enriched only by the first generations of massive stars. By analyzing the light from these stars with powerful spectrographs, astronomers can read their chemical composition. Stars that are incredibly metal-poor, meaning they contain very low amounts of elements heavier than hydrogen and helium, are necessarily ancient, forged before many supernovae had a chance to seed the cosmos with heavier elements. The precise locations and orbits of these ancient stars within a galaxy like our Milky Way tell a violent story of the galaxy's assembly. They are often found on chaotic, plunging orbits that suggest they were not born here, but were instead stolen from smaller dwarf galaxies that our galaxy cannibalized billions of years ago. Each of these stellar streams and clusters is a chapter in the autobiography of our galaxy, a silent witness to the hierarchical growth that built the cosmic web from the bottom up. Beyond individual stars, we can also find the fossilized remains of entire galactic building blocks. Imagine a small group of galaxies that fell into a developing cluster very early in the universe's history. The intense gravitational tides within the dense cluster environment would have quickly ripped apart the smallest, weakest galaxies, dispersing their stars into a faint, diffuse cloud of light that permeates the space between the brighter cluster galaxies. This faint glow, known as intracluster light, is the skeletal remains of those long-dead galaxies. It is incredibly difficult to detect, requiring exceptionally dark skies and long exposures with the world's most powerful telescopes. But its discovery provides direct evidence of the violent merger history that built the massive clusters we see at the web's nodes. Similarly, astronomers sometimes discover fossil groups, which are seemingly single, giant elliptical galaxies sitting in the center of a massive dark matter halo. These are not solitary giants. They are the end products of a complete merger of an entire group of galaxies, where one dominant galaxy has consumed all of its former companions, leaving behind only the X-ray glow of the hot gas that was once shared between them. These fossils are the smoking gun for the hierarchical process, the quiet aftermath of a cosmic feast that occurred long ago. This painstaking archaeological work does not happen in isolation. It exists in a powerful symbiotic relationship with the digital universes created by supercomputer simulations. The simulations, like the Millennium and Illustris projects, provide the theoretical framework and the movie of how structure should form according to our physical laws. They make specific predictions: how many stellar streams should be wrapped around a galaxy like ours, how much intracluster light should glow in a mature cluster, how the chemical abundances should change over time. Cosmic archaeologists then take these predictions and scour the real universe with their telescopes, searching for the actual evidence. When they find a stellar stream with exactly the properties a simulation predicted, it is a moment of profound validation. When they discover something the simulations did not predict, a fossil group that is too large or a stellar population that is too ancient, it sends the theorists back to their computers to refine their models. This back and forth between digital prediction and real-world observation is the engine that drives our understanding forward, allowing us to slowly but surely piece together the complete history of the cosmic web, from its quantum seeds in the first instant of time to the magnificent, evolving architecture we are part of today. Yet for all the data, the simulations, and the complex physics, the true power of these discoveries lies not just in what they tell us about the universe, but in what they tell us about ourselves. Contemplating the sheer scale of the cosmic web with its billion light-year filaments and immense voids does something profound to the human spirit. It evokes a dual sensation that is both humbling and exhilarating, a feeling of being infinitesimally small, yet paradoxically privileged to be the part of the universe that has become conscious and can understand its own immensity. This is more than just science. It is a deeply philosophical and cultural moment for our species, reshaping our identity and our place in the grand scheme of things. This sense of awe is perhaps best captured by the late astronomer Carl Sagan, whose poetic reflections have guided millions on this journey of cosmic perspective. In his iconic series Cosmos, he presented the now famous image of our pale blue dot, a speck of dust suspended in a sunbeam, but his wisdom extends even further to these vast structures. He once reflected that we are a way for the cosmos to know itself, that the hydrogen atoms in our bodies were forged in the hearts of ancient stars and the explosions of supernova. When we map the cosmic web, we are not just exploring something external to us, we are tracing our own deepest ancestry. We are the universe becoming self-aware, looking back at its own magnificent architecture and trying to decipher its own origins. This perspective dissolves the artificial boundary between the observer and the observed, placing us not as separate from the cosmos, but as an integral, conscious part of its ongoing story. This profound shift in perspective ripples far beyond the confines of the scientific community, deeply influencing our culture, our art, and our collective imagination. For centuries, artists have looked to the night sky for inspiration, but the discovery of these invisible, massive structures has added a new layer of depth to their work. Modern digital artists create stunning visualizations of the cosmic web, transforming cold data into swirling, intricate tapestries of light and dark that evoke a sense of wonder and mystery. Writers and filmmakers weave these concepts into narratives that explore not just space travel, but the nature of reality itself, asking questions about our significance within such an unimaginably vast and structured reality. These artistic interpretations are not mere illustrations. They are a vital part of the human conversation about these discoveries, helping us to process and emotionally engage with concepts that our rational minds can scarcely grasp. The drive to understand this architecture has also become a powerful catalyst for global cooperation and technological innovation. A project like the Sloan Digital Sky Survey or the upcoming Vera-C. Rubin Observatory is not the work of a single nation. It is a monumental international effort, bringing together thousands of scientists, engineers, and programmers from across the globe. The shared goal of mapping the universe transcends political and cultural differences, uniting humanity in a common, peaceful quest for knowledge. The technological challenges involved, from building cameras with billions of pixels to developing algorithms that can process petabytes of data, push the boundaries of computing and engineering, creating spin-off technologies that benefit society in countless other ways. The quest to understand the cosmic web, therefore, is not an isolated academic pursuit. It is a testament to what humanity can achieve when we collaborate on a grand scale, driven by shared curiosity and wonder. So the next time you find yourself under a clear, dark night sky, take a moment to truly look up. The stars you see are the most local and visible part of this story, but now you know they are just the glittering tips of a far deeper iceberg. Trace the faint band of the Milky Way, our home galaxy, and then let your imagination push beyond it. Picture the invisible river of gravity that is carrying our galaxy toward the great attractor. Envision the vast, empty deserts of the cosmic voids and the brilliant, crowded cities of galaxy clusters at the intersections of the web. That faint smudge of the Andromeda Galaxy is not just a distant spiral. It is our future collision partner, a chapter in the ongoing story of our local group's journey within the Laniakea Supercluster. This act of personal connection, of linking the beauty you can see with the incredible science that reveals what you cannot, is where the journey becomes truly personal. It transforms the abstract into the experiential, allowing you to feel your own place within this grand cosmic design, a participant in a story 13.8 billion years in the making. But perhaps the most profound impact of this educational outreach lies in its ability to democratize discovery itself. For centuries, cosmology was the domain of a select few with access to powerful telescopes and advanced degrees. Today, that paradigm has completely shifted. A retired teacher in Wisconsin can log into Zooniverse and help identify gravitational lenses, the telltale smears of light that reveal the presence of dark matter. A high school student in Brazil can download a universe simulator and watch a digital cosmos evolve over billions of years on their laptop. These tools shatter the ivory tower, transforming the majestic and sometimes intimidating narrative of the universe into a participatory story that everyone can help write. This is no longer just about learning facts. It is about contributing to the very process of science, about being part of the global community that is actively piecing together the grand puzzle of existence. It proves that the journey beyond the Gassy Mountains is not a solitary expedition for a few elite explorers, but a shared human adventure, one where curiosity is the only passport required. Now, as we marvel at these cosmic leviathans, it's crucial to separate the breathtaking science from the common misconceptions that often swirl around such mind-bending discoveries. One of the most persistent myths is the idea that these massive structures somehow disprove the Big Bang theory. The reasoning goes that if the universe started from a single, infinitely dense point, it should have expanded into a perfectly smooth, featureless void. The existence of giant walls and vast voids, therefore, seems to contradict this origin story, But this is a fundamental misunderstanding. The Big Bang Theory doesn't predict a perfectly uniform universe. In fact, it absolutely requires the opposite. Those tiny quantum fluctuations in the primordial universe, the very seeds of all structure that we see imprinted in the cosmic microwave background, are a predicted and essential part of the model. The great walls and filaments aren't evidence against the Big Bang. They are the direct, magnificent consequence of it, amplified over billions of years by gravity. The real story isn't one of contradiction, but of glorious, detailed confirmation. Another common misconception is that these structures imply a center to the universe, or even worse, that we might be near it. When we look at a map of the Sloane Great Wall, it's easy to fall into that trap. It looks like a giant structure over there, which might make us feel like we're looking at it from some privileged central vantage point. This is another trick of perspective. A much better analogy is to think of the universe as a giant raisin cake baking in the oven. As the cake rises, every single raisin moves away from every other raisin. There is no center to the surface of the cake. From the perspective of any raisin, all the others are receding. Now, in our cosmic cake, the raisins are galaxy clusters, and the dough is the fabric of space-time. The key insight is that while the raisins might be clustered in some areas, maybe a few stuck together, or a large clump on one side, the overall distribution of raisins, when you zoom out to see the entire cake, is still fairly even. The cosmic web is those local clusters and clumps of raisins. Yes, from our lonely raisin, the clump a few inches away looks huge and significant. But if you could step back and see the whole oven, you'd see that those clumps are scattered everywhere, and no single raisin has a special central position. The cosmological principle holds on the very largest scales. The universe is homogeneous, even if it's richly structured and lumpy in our local neighborhood. This is why the work of science communicators and dedicated astronomers is so vital. Experts like Dr. Katie Mack, a theoretical cosmologist, often emphasize that the existence of these cosmic giants doesn't break cosmology, it makes it more interesting. The anomalies and puzzles, like the potential scale of the Hercules corona Borealis Great Wall, are not causes for panic or for throwing out our well-tested models. Instead, they are the exciting frontiers of research, the mysteries that propel science forward. They are the questions that keep astronomers up at night, not with worry, but with thrilling anticipation for what the next dataset might reveal. This nuanced approach is essential for combating the spread of misinformation, which often preys on a simplified, black and white view of science. The reality is far more beautiful, a robust, evidence-based core of understanding that is constantly being refined and sometimes revolutionized at the edges by new, unexpected discoveries. Ultimately, this journey through the cosmic web equips us with more than just facts about the universe. It strengthens our critical thinking muscles. In an age flooded with information, the ability to discern solid, evidence-based science from captivating speculation is an invaluable skill. It teaches us to be comfortable with uncertainty, to understand that a mystery is not a failure but an invitation to learn more. When we look up at the night sky, we can now appreciate not just the beauty of the stars, but the profound, layered architecture that lies beyond, confident in our understanding that its existence doesn't diminish the Big Bang but completes its story, and that our place within it, while not central, is uniquely privileged with the capacity to understand it all. Confronting the sheer scale of the cosmic web, with its filaments spanning billions of light years and its voids of breathtaking emptiness, forces upon us a series of profound and deeply personal questions. If our entire galaxy is but a speck of dust on a single strand of this immeasurable web, and our planet a mere microscopic point upon that speck, then what possible significance can our lives hold? This line of inquiry, born from the very science that reveals this grandeur, is not a new one. It is a modern incarnation of an ancient philosophical struggle, often called the problem of cosmic insignificance. The raw data could lead one to a bleak conclusion. In a universe of such vast, impersonal forces and incomprehensible scale, nothing we do ultimately matters. Our triumphs and tragedies, our art and our wars, all play out on a stage so small as to be utterly inconsequential from a galactic, let alone a universal, perspective. This is the potential for existential dread that the cosmos presents, a chilling indifference that can feel isolating. Yet, the most compelling perspectives from scientists and philosophers who have grappled with this very idea point us toward a radically different and far more beautiful interpretation. They argue that this scale does not diminish our value, but instead redefines and elevates it. The astrophysicist Neil deGrasse Tyson has become a leading voice for what he terms the cosmic perspective. He reframes our understanding not as a lesson in insignificance, but in rarity and preciousness. He asks us to consider that the very atoms that constitute our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe, were forged in the nuclear furnaces of massive stars that lived and died billions of years ago. These stellar remnants were then scattered across space by supernova explosions, eventually finding their way into a nascent cloud of gas and dust that coalesced into our solar system and ultimately into us. From this viewpoint, we are not separate from the cosmos, we are a product of it. We are the universe become conscious, a way for the cosmos to look back upon itself and contemplate its own origins and majesty. Our ability to understand the laws of physics, to build telescopes that can peer back to the dawn of time, to map the invisible dark matter scaffolding of existence, these are not trivial feats of a meaningless species. They are profound expressions of a universe awakening to its own nature. This shifts the narrative from one of isolation to one of deep, fundamental connection. This cosmic perspective, when fully embraced, carries with it a powerful ethical imperative. When we look at Earth from this vantage point, not as a collection of separate nations, but as a fragile, pale blue dot suspended in a sunbeam, as Carl Sagan so famously described it, the artificial boundaries that divide humanity seem to vanish. The conflicts, prejudices, and political squabbles that consume so much of our energy are revealed for what they are: trivialities played out on a tiny, vulnerable world adrift in an impossibly vast and mostly inhospitable void. This realization has the potential to be the greatest unifier in human history, fostering a sense of global citizenship and shared destiny. If we are alone in this cosmic desert, then our planet and the life it holds are incalculably precious. If we are not alone, then the way we steward our world becomes a testament to what an intelligent, conscious civilization can achieve. This awareness naturally extends to an urgent call for environmental stewardship. Our atmosphere, our oceans, and our biosphere are not just our home. They are a rare and delicate oasis, the only one we know of for certain. Understanding our place in the structured universe doesn't give us license to exploit our world with abandon. It charges us with the profound responsibility to protect it, for we are the guardians of a singular, miraculous experiment in complexity and consciousness. Ultimately, this journey through the cosmic web is more than an intellectual exercise. It is an invitation to a personal and transformative shift in consciousness. It asks us to hold two seemingly contradictory truths in our minds at once: the truth of our physical smallness and the truth of our existential grandeur. We are simultaneously inconsequential dust and star stuff become conscious. This duality is not a paradox to be solved, but a perspective to be lived. It can fill us with a profound sense of humility. curbing our arrogance and reminding us that we are part of a much larger, older, and more mysterious whole. And yet, it can also fill us with an incredible sense of purpose. Our brief moment of awareness in the vast timeline of the universe is our opportunity to learn, to create, to love, and to care for our tiny world. The ethical choice, then, is to use this cosmic perspective not as a reason for despair, but as a catalyst for wonder, for compassion, and for action. It challenges us to live our lives with a greater sense of connection, to value our shared humanity, and to strive to leave a legacy of knowledge and care on this pale blue dot, our only home in the immensity of the structured cosmos. The best part about this incredible journey is that you don't need a billion-dollar telescope to participate in it. The tools to explore this cosmic architecture for yourself are available to anyone with an internet connection, transforming you from a passive viewer into an active cosmic cartographer. Let's start with the familiar night sky. A wonderful free planetarium software called Stellarium is your perfect first step. It's available as a web app or a desktop download, and it does more than just show you what stars are overhead tonight. You can use its search function to find not just planets and stars, but entire galaxies. Type in Andromeda Galaxy, and the view will swing to our nearest major galactic neighbor. Now zoom in. As you do, remember that you're not just looking at a fuzzy patch of light. You're seeing the trillions of stars that make up the largest galaxy in our local group, a key piece of our local filament in the cosmic web. From there, search for Virgo cluster. The view will jump to a dense region in the constellation Virgo. While it will just look like a field of stars, Stellarium is showing you the heart of the massive cluster that anchors our supercluster, a gravitational titan pulling us inward. This simple act of locating these objects on a digital sky map is the first step in internalizing the three-dimensional reality of our universe. To truly grasp the scale of what we've been discussing, you need to move beyond the virtual sky and into the actual data that astronomers use. This is where the Sloan Digital Sky Survey, or SDSS, opens a breathtaking portal. Head to their website and find the iconic Navigate tool. This isn't a simulation, it's a direct interface to the telescope's data. You'll be presented with a seemingly random field of stars, but look closer. Many of the stars have strange, colorful halos around them. These are not stars at all, but distant galaxies whose light has been captured by the survey. Click on one. Instantly, you'll get a wealth of information. Its distance in megaparsecs, its redshift value, and even a spectrum showing the specific fingerprint of its light. Now try this. Find a galaxy, note its redshift a value like 0.05, and then search for another galaxy with a higher redshift like 0.1. The tool will show you that the second galaxy is billions of light years farther away. You are now directly interacting with the redshift-distance relationship, the fundamental tool that allowed us to build the three-dimensional map of the universe and discover the Great Walls in the first place. You can spend hours flying through these galaxy fields, each dot a magnificent island universe, and in doing so, you are literally browsing the cosmic web. For a more guided, visceral experience of flying through this vast data, YouTube is an incredible resource. Channels like Hubble Space Telescope and ESA Hubble offer official, breathtaking visualizations, but seek out the work of dedicated digital artists and scientists as well. Search for terms like Cosmic Web Simulation Fly-Through or Sloan Digital Sky Survey Visualization. You will find videos that take the actual SDSS data and animate it, transforming those static dots of galaxies into a dynamic, three-dimensional model that you can soar through. Watch one of these videos and you will see the filaments and walls emerge before your eyes. You'll witness the camera zooming out from our local group, past the Virgo cluster, and out to the staggering scale of Laniakea, all set to epic, awe-inspiring music. This isn't just watching a documentary. It's an experiential journey that helps your brain comprehend the impossible scales we've been talking about. It makes abstract concepts tangible and fills you with the same sense of wonder that the original researchers must have felt. Perhaps the most inspiring way to engage is to contribute to real science yourself through citizen science projects. Platforms like Zooniverse host numerous astronomy projects where professionals need help sifting through massive datasets. You could be part of the team that classifies galaxies from telescope images for the Galaxy Zoo project, helping to identify rare mergers or strange morphological types that might warrant further study. There's a famous story from the early days of Galaxy Zoo about a Dutch schoolteacher named Hanny van Arkel. While classifying galaxies, she noticed a strange, glowing green object near a galaxy that didn't match any known classification. She posted it on the project's forum, and it sparked immediate interest from astronomers. This object became known as Hanny's voorwerp, Dutch for Hanny's object, and it turned out to be a completely new astronomical phenomenon, a light echo from a quasar, a ghostly cloud of gas illuminated by a burst of energy from a supermassive black hole. Her discovery, made from her home computer, led to published scientific papers and a new avenue of astrophysical research. Her story is a powerful testament to the fact that discovery is no longer confined to those with a PhD. With curiosity and access to the right tools, anyone can literally stumble upon a new cosmic mystery. Your own moment of discovery could be just a few clicks away, waiting for you in the data of a sky survey, reminding you that the adventure of exploring the universe is an open invitation to us all. Yet for all the breathtaking progress we've made in mapping the cosmic web, the most thrilling part of this story is that it is far from over. In many ways, the grand maps created by surveys like Sloane have not given us all the answers. Instead, they have handed us a new, more profound set of questions, a list of cosmic anomalies and puzzles that now define the very frontier of cosmological research. These are not small, trivial gaps in our knowledge, but fundamental mysteries that strike at the core of our understanding of physics itself, and how we resolve them could very well lead to the next great revolution in science. At the very top of this list is the urgent, pressing question of scale. Is there a fundamental upper limit to how large a structure in the universe can be? Our standard cosmological model, the lambda cold dark matter model, provides a theoretical prediction based on the universe's age and the expected rate of gravitational growth. This model suggests that nothing should be able to grow much larger than about 1.2 billion light-years across, and yet we keep finding candidates that appear to shatter this limit. The Sloan Great Wall nudges against it at 1.4 billion light-years. The Hercules Corona Borealis Great Wall and the huge large quasar group, should they be confirmed as single structures, would utterly demolish it, suggesting sizes of up to 10 billion light-years. This is the central tension in cosmology right now. Are these objects statistical flukes, mere illusions created by our limited perspective, or are they screaming evidence that our model is missing a crucial piece of physics? The answer will likely come from the next generation of telescopes. The Vera Rubin Observatory's legacy survey of space and time will map billions of galaxies with unprecedented precision, allowing us to perform statistical analyses so powerful that they will finally determine, once and for all, if these cosmic giants are real. This isn't just about cataloging record breakers. It is a direct test of whether our most fundamental assumption about the universe, that it is homogeneous on the largest scales, is actually true. Closely tied to this is the enigmatic interplay between the universe's two greatest unknowns, dark matter and dark energy. We understand their roles in broad strokes. dark matter builds the web, dark energy stretches it apart, but the precise mechanics remain maddeningly elusive. We still do not know what dark matter is made of. Is it a heavy, slow-moving particle, as the cold dark matter suggests? Or could it be a warmer, faster-moving particle that would change how quickly the first structures formed? The answer is written into the very fine details of the cosmic web, in the number of tiny dwarf galaxies surrounding larger ones and the exact properties of the faintest filaments. Similarly, is dark energy truly a constant force, as Einstein's cosmological constant suggests, or does its strength vary over time or across space? The way the cosmic web evolves, how quickly clusters stop accreting new galaxies, and how the voids expand holds the key. Every new massive structure we find adds a new data point to this cosmic tug-of-war, helping us to refine our equations and understand the balance of power between construction and dissolution in our universe. And then we have the puzzles that pop up in our own celestial backyard, challenging us to explain not just the distant universe, but our immediate place within it. A stunning recent example is the discovery of the giant arc, a nearly symmetrical array of galaxies, galaxy clusters, and gas that stretches an incredible 3.3 billion light-years across, discovered by astronomer Alexia Lopez by looking at the light of distant quasars. Its immense size and seemingly coordinated structure are deeply puzzling. Equally compelling is the KBC void, named after astronomers Keenan, Barger, and Cowie, which suggests that our Milky Way galaxy resides inside an underdense region, a local void that is significantly larger than predicted. If true, this could mean our local measurements of the universe's expansion rate are biased, potentially explaining the growing tension between different methods of calculating the Hubble constant. These are not just abstract curiosities, they are potential systematic errors that could be skewing our entire view of the cosmos, reminding us that our vantage point from within a specific structural environment might be coloring our perception of the whole. The optimism within the scientific community in the face of these great mysteries is palpable. Leading cosmologists like J. Richard Gott, who helped pioneer the mapping of the large-scale structure, often express a sense of excitement rather than frustration. He has likened the process to being an explorer who has just discovered a new continent. The first rough maps are drawn, but the real work of understanding its rivers, mountains, and ecology is just beginning. This sentiment is echoed by researchers like Lisha Verd, a professor of cosmology, who has said that anomalies are not the death knell of a theory, but the sign of a healthy science on the verge of a breakthrough. The greatest discoveries in physics have always come from such points of tension from the orbit of Mercury that couldn't be explained by Newtonian gravity to the ultraviolet catastrophe that gave birth to quantum mechanics. The inconsistencies we see in the cosmic web today could be the very clues that lead us to a deeper theory of gravity, one that might finally reconcile the quantum world with the cosmic scale, or even reveal a new understanding of the dark sectors that dominate our universe. This is the beautiful, unfolding saga of discovery. We are no longer simply mapping the universe, we are stress testing our most fundamental theories against its grandest structures. Every anomalous wall, every peculiar void, is a question posed by nature, and with powerful new tools like the Euclid Space Telescope and the Square Kilometre Array coming online, we are finally equipping ourselves to listen for the answers. The journey beyond the gassy mountains has revealed a cosmos far stranger and more structured than we ever imagined, and the path forward promises to be even more astonishing. And so our journey, which began with the beautiful but deceptively local clouds of gas and dust we call nebulae, has carried us across scales of space and time that truly defy human comprehension. We have ventured from the stellar nurseries of Orion, measured in mere dozens of light years, to the incomprehensible Leviathans of the cosmic web filaments and walls like the Sloan Great Wall, stretching over 1 billion light years, and the controversial, rule-breaking Hercules Corona Borealis Great Wall that challenges the very foundations of cosmology itself. We have mapped the vast, silent deserts of cosmic voids and found our own address within the flowing supercluster of Laniakea, pulled by the hidden gravitational might of the great Attractor. Each step in this voyage has not simply added a new object to a catalogue. It has fundamentally rewritten our understanding of the universe's architecture, revealing a cosmos that is not a random scattering of stars but a highly structured, dynamic, and evolving web of relationships on the grandest possible scale. This breathtaking new view of reality is not the product of any single genius working in isolation, but the culmination of a truly global, collaborative human endeavor. It is a story of patient, meticulous work by thousands of scientists across generations and continents, from the early cartographers like Margaret Geller and John Huckra, who first glimpsed the Great Wall, to the vast international teams behind the Sloan Digital Sky Survey and the Planck satellite. It is a narrative powered by a technological revolution where advancements in digital cameras, spectroscopy, and supercomputing have acted as a collective lens, allowing us to see farther, map more deeply, and simulate more accurately than ever before. We have moved from hand-plotted graphs of galaxies to stunning three-dimensional visualizations of the dark matter cosmos, from theoretical predictions to the confident detection of the primordial seeds of structure in the cosmic microwave background. This synergy of human curiosity and technological ingenuity has gifted us with a cosmic perspective that was unimaginable just a century ago. The astrophysicist Hubert Reeves offered a beautiful reflection on this entire endeavor when he said, "We are stardust brought to life, then empowered by the universe to figure itself out, and we have only just begun." This poetic truth captures the profound duality of our place in the cosmos. We are, quite literally, made from the ashes of dead stars, temporary assemblies of atoms granted a fleeting moment of consciousness. And yet, with these minds forged from stardust, we have begun to decode the universe's deepest secrets, to trace the invisible scaffolding of dark matter, and to measure the ghostly influence of dark energy. We have embarked on the universe's great project of self-awareness. Reeves's closing point, "and we have only just begun," is perhaps the most exciting part of all. For every question we have answered, a dozen more have emerged. The mysteries of dark matter and dark energy remain. The true scale of the largest structures is still debated, and the next generation of telescopes promises to reveal even deeper layers of this cosmic onion. This is not an ending, but an invitation. The greatest takeaway from this voyage is that the universe is not a static picture to be fully understood, but a dynamic, unfolding story in which we are both participants and narrators. So I encourage you to carry this sense of wonder with you. The next time you find yourself under a clear night sky, look up, see beyond the familiar stars to the hidden architecture that connects them. Remember that you are standing on a pale blue dot, nestled within a galaxy that is itself riding a gravitational current through the grand supercluster of Laniakea, part of a web that spans the entire observable universe. Stay curious, keep asking questions, and never stop marveling at the fact that we are here, we are aware, and we are only just beginning to figure it all out. The journey beyond the gassy mountains continues, and the next great discovery awaits. Thank you so much for joining me on this incredible voyage across the cosmos, from the beautiful gassy mountains of our own galactic backyard to the very edges of the observable universe and its most massive, mind-bending structures. If this journey sparked your sense of wonder, Be sure to hit the like button and subscribe to the channel. It truly helps us continue creating deep dives into the universe's greatest mysteries. Don't forget to tap that notification bell so you never miss an exploration into the unknown. Now, I want to hear from you. Down in the comments, tell me which of these cosmic leviathans captured your imagination the most. Was it the sheer scale of the Sloan Great Wall, the mysterious pull of the Great Attractor, or the rule-breaking potential of the Hercules Corona Borealis Great Wall? What burning cosmic question should we tackle in a future video? Your thoughts and curiosity are what make this community so special, and they often inspire the topics we explore next. If you're eager to continue this journey on your own, I highly recommend diving into some incredible books that bring this science to life. For a breathtaking overview of the cosmic web, J. Richard Gott's The Cosmic Web, Mysterious Architecture of the Universe is a fantastic read. And for a deeper look at the people and discoveries behind these revelations, Richard Payneck's The 4% Universe, Dark Matter, Dark Energy, and the Race to Discover the Rest of Reality reads like a thrilling detective story. For those who love visual explorations, the documentary How the Universe Works has some phenomenal episodes on large-scale structure, and the YouTube channel PBS Space-Time offers deep, yet accessible, dives into the physics behind it all. This journey doesn't end when this video does. The greatest tool for exploration is your own curiosity. So from all of us here, keep looking up, keep asking questions, and never stop wondering. The universe has endless, breathtaking wonders waiting for you, and we can't wait to discover